Preface and Table of Contents of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Familiar Letters on Chemistry and its relation to commerce, physiology, and agriculture by Justus LIEBIG, M.D., Ph.D., F.R.S., Professor of Chemistry in the University of Gießen. Edited by John Gardner, M.D. Preface. The letters contained in this little volume embrace some of the most important points of the science of chemistry, in their application to natural philosophy, physiology, agriculture, and commerce. Some of them treat of subjects which have already been, or will hereafter be, more fully discussed in my larger works. They were intended to be mere sketches, and were written for the especial purpose of exciting the attention of governments and an enlightened public to the necessity of establishing schools of chemistry, and of promoting by every means the study of a science so intimately connected with the arts, pursuits, and social well-being of modern civilized nations. For my own part, I do not scruple to avow the conviction that ere long a knowledge of the principal truths of chemistry will be expected in every educated man, and that it will be as necessary to the statesman, the political economist, and the practical agriculturalist as it is already indispensable to the physician and the manufacturer. In Germany, such of these letters as have already been published have not failed to produce some of the results anticipated. New professorships have been established in the universities of Göttingen and Würzburg for the express purpose of facilitating the application of chemical truths to the practical arts of life, and of following up the new line of investigation and research, the bearing of chemistry upon physiology, medicine, and agriculture, which may be said to be only just begun. My friend Dr. Ernest Diefenbach, one of my first pupils, who is well acquainted with all the branches of chemistry, physics, natural history, and medicine, suggested to me that a collection of these letters would be acceptable to the English public, which has so favorably received my former works. I readily acquiesced in the publication of an English edition, and undertook to write a few additional letters, which should embrace some conclusions I have arrived at, in my recent investigations, in connection with the application of chemical science to the physiology of plants and agriculture. My esteemed friend Dr. Gardner has had the kindness to revise the manuscript and the proof sheets for publication, for which I cannot refrain expressing my best thanks. It only remains for me to add a hope that this little offering may serve to make new friends to our beautiful and useful science, and be a remembrancer to those old friends who have for many years past taken a lively interest in all my labors. Justus LIEBIG, Gießen, August 1843. Contents. Letter 1. The subject proposed. Materials employed for chemical apparatus. Glass, caoutchouc, cork, platinum. The balance. The elements of the ancients represent the forms of matter. Lavoisier and his successors. Study of the materials composing the earth. Synthetic production of minerals, lapis lazuli. Organic chemistry. Letter 2. Changes of form which every kind of matter undergoes. Conversion of gases into liquids and solids. Carbonic acid, its curious properties in a solid state. Condensation of gases by porous bodies. By spongy platinum. Importance of this property in nature. Letter 3. The manufacture of soda from culinary salt. Its importance in the arts and in commerce. Glass, soap, sulfuric acid, silver refining, bleaching, trade in sulfur. Letter 4. Connection of theory with practice. Employment of magnetism as a moving power. Its impracticability. Relation of coals and zinc as economic sources of force. Manufacture of beetroot sugar. Its impolicy. Gas for illumination. Letter 5. Isomerism, or identity of composition in bodies with different chemical and physical properties. Crystallization, amorphism. Isomorphism, or similarity of properties in bodies totally different in composition. Letter 6. Alliance of chemistry with physiology. Division of food into nourishment and materials for combustion. Effects of atmospheric oxygen. Balance of carbon and oxygen. Letter 7. Animal heat. Its laws and influence on the animal functions. Loss and supply. Influence of climate. Fuel of animal heat. Agency of oxygen in disease. Respiration. Letter 8. Aliments. Constituents of the blood. Fibrin, albumin, inorganic substances. Isomerism of fibrin, albumin, and elements of nutrition. Relation of animal and vegetable organisms. Letter 9. Growth of animals. Uses of butter and milk. Metamorphoses of tissues. Food of carnivora and of the horse. Letter 10. Application of the preceding facts to man. Division of human food. Uses of gelatin. Letter 11. Circulation of matter in the animal and vegetable kingdoms. The ocean. Agriculture. Restitution of an equilibrium in the soil. Causes of the exhaustion of land. Virginia, England. Relief gained by importation of bones. Empirical farming unsatisfactory. Necessity for scientific principles. Influence of the atmosphere. Of saline and earthy matters in the soil. Letter 12. Science and art of agriculture. Necessity of chemistry. Rationale of agricultural processes. Washing for gold. Letter 13. Illustration of the necessity of chemistry to advance and perfect agriculture. Manner in which fallow ameliorates the soil. Uses of lime. Effects of burning. Of marl. Letter 14. Nature and effects of manures. Animal bodies subject to constant waste. Parts separating. Exuviae, waste vegetable matters, together contain all the elements of the soil and of food. Various value of excrements of different animals as manure. Letter 15. Source of the carbon and nitrogen of plants. Produce of carbon in forests and meadows supplied only with mineral aliments prove it to be from the atmosphere. Relations between mineral constituents and carbon and nitrogen. Effects of the carbonic acid and ammonia of manures. Necessity of inorganic constituents to the formation of aliments, of blood, and therefore of nutrition. Necessity of inquiries by analysis to advance agriculture. Letter 16. Results of the author's latest inquiries. Superlative importance of the phosphates of lime and alkalis to the cultivation of the cerealia. Sources of a supply of these materials. End of Table of Contents.
Section 1 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Familiar Letters on Chemistry by Justus Liebig. Letter number 1. My dear Sir, the influence which the science of chemistry exercises upon human industry, agriculture, and commerce, upon physiology, medicine, and other sciences, is now so interesting a topic of conversation everywhere, that it may be no unacceptable present to you if I trace in a few familiar letters some of the relations it bears to these various sciences, and exhibit for you its actual effect upon the present social condition of mankind. In speaking of the present state of chemistry, its rise and progress, I shall need no apology if, as a preliminary step, I call your attention to the implements which the chemist employs, the means which are indispensable to his labors and to his success. These consist generally of materials furnished to us by nature, endowed with many most remarkable properties fitting them for our purposes. If one of them is a production of art, yet its adaptation to the use of mankind, the qualities which render it available to us, must be referred to the same source as those derived immediately from nature. Cork, platinum, glass, and caoutchouc are the substances to which I allude, and which minister so essentially to modern chemical investigations. Without them, indeed, we might have made some progress, but it would have been slow. We might have accomplished much, but it would have been far less than has been done with their aid. Some persons, by the employment of expensive substances, might have pursued the science, but incalculably fewer minds would have been engaged in its advancement. These materials have only been duly appreciated and fully adopted within a very recent period. In the time of Lavoisier, the rich alone could make chemical researches. The necessary apparatus could only be procured at a very great expense. And first, of glass. Everyone is familiar with most of the properties of this curious substance: its transparency, hardness, destitution of color, and stability under ordinary circumstances. To these obvious qualities we may add those which are specially adapted to the use of the chemist, namely, that it is unaffected by most acids or other fluids contained within it. At certain temperatures it becomes more ductile and plastic than wax, and may be made to assume in our hands, before the flame of a common lamp, the form of every vessel we need to contain our materials, and of every apparatus required to pursue our experiments. Then how admirable and valuable are the properties of cork! How little do men reflect upon the inestimable worth of so common a substance! How few rightly esteem the importance of it to the progress of science and the moral advancement of mankind! There is no production of nature or art equally adapted to the purposes to which the chemist applies it. Cork consists of a soft, highly elastic substance as a basis, having diffused throughout a matter with properties resembling wax, tallow, and resin, yet dissimilar to all of these, and termed suberin. This renders it perfectly impermeable to fluids, and, in a great measure, even to gases. It is thus the fittest material we possess for closing our bottles and retaining their contents. By its means, and with the aid of caoutchouc, we connect our vessels and tubes of glass, and construct the most complicated apparatus. We form joints and links of connection, adapt large apertures to small, and thus dispense altogether with the aid of the brass founder and the mechanist. Thus the implements of the chemist are cheaply and easily procured, immediately adapted to any purpose, and readily repaired or altered. Again, in investigating the composition of solid bodies, of minerals, we are under the necessity of bringing them into a liquid state, either by solution or fusion. Now vessels of glass, of porcelain, and of all non-metallic substances are destroyed by the means we employ for that purpose, are acted upon by many acids, by alkalis and the alkaline carbonates. Crucibles of gold and silver would melt at high temperatures, but we have a combination of all the qualities we can desire in platinum. This metal was only first adapted to these uses about 50 years since. It is cheaper than gold, harder and more durable than silver, infusible at all temperatures of our furnaces, and is left intact by acids and alkaline carbonates. Platinum unites all the valuable properties of gold and of porcelain, resisting the action of heat and of almost all chemical agents. As no mineral analysis could be made perfectly without platinum vessels, had we not possessed this metal, the composition of minerals would have yet remained unknown. Without cork and caoutchouc, we should have required the costly aid of the mechanician at every step. Even without the latter of these adjuncts, our instruments would have been far more costly and fragile. Possessing all these gifts of nature, we economize incalculably our time, to us more precious than money. Such are our instruments. An equal improvement has been accomplished in our laboratory. This is no longer the damp, cold, fireproof vault of the metallurgist, nor the manufactory of the druggist, fitted up with stills and retorts. On the contrary, a light, warm, comfortable room, where beautifully constructed lamps supply the place of furnaces, and the pure and odorless flame of gas, or of spirits of wine, supersedes coal and other fuel, and gives us all the fire we need, where health is not invaded, nor the free exercise of thought impeded. There we pursue our inquiries, and interrogate nature to reveal her secrets. To these simple means must be added the balance, and then we possess everything which is required for the most extensive researches. The great distinction between the manner of proceeding in chemistry and natural philosophy is, that one weighs, the other measures. The natural philosopher has applied his measures to nature for many centuries, but only for 50 years have we attempted to advance our philosophy by weighing. For all great discoveries, chemists are indebted to the balance, that incomparable instrument which gives permanence to every observation, dispels all ambiguity, establishes truth, detects error, and guides us in the true path of inductive science. The balance, once adopted as a means of investigating nature, put an end to the school of Aristotle in physics. The explanation of natural phenomena by mere fanciful speculations gave place to a true natural philosophy. Fire, air, earth, and water could no longer be regarded as elements. 3 of them could henceforth be considered only as significative of the forms in which all matter exists. Everything with which we are conversant upon the surface of the earth is solid, liquid, or aeriform. But the notion of the elementary nature of air, earth, and water so universally held was now discovered to belong to the errors of the past. Fire was found to be but the visible and otherwise perceptible indication of changes proceeding within the so-called elements. Lavoisier investigated the composition of the atmosphere and of water, and studied the many wonderful offices performed by an element common to both in the scheme of nature, namely oxygen, and he discovered many of the properties of this elementary gas. After his time, the principal problem of chemical philosophers was to determine the composition of the solid matters composing the earth. To the 18 metals previously known were soon added 24 discovered to be constituents of minerals. The great mass of the earth was shown to be composed of metals in combination with oxygen, to which they are united in 1, 2, or more definite and unalterable proportions, forming compounds which are termed metallic oxides, and these, again, combined with oxides of other bodies, essentially different to metals, namely carbon and silicon. If to these we add certain compounds of sulfur with metals, in which the sulfur takes the place of oxygen and forms sulfurets, and one other body, common salt, which is composed of sodium and chlorine, we have every substance which exists in a solid form upon our globe in any very considerable mass. Other compounds, innumerably various, are found only in small scattered quantities. The chemist, however, did not remain satisfied with the separation of minerals into their component elements, that is, their analysis, but he sought by synthesis, that is, by combining the separate elements and forming substances similar to those constructed by nature, to prove the accuracy of his processes and the correctness of his conclusions. Thus he formed, for instance, pumice stone, feldspar, mica, iron pyrites, etc., artificially. But of all the achievements of inorganic chemistry, the artificial formation of lapis lazuli was the most brilliant and the most conclusive. This mineral, as presented to us by nature, is calculated powerfully to arrest our attention by its beautiful azure blue color, its remaining unchanged by exposure to air or to fire, and furnishing us with a most valuable pigment, ultramarine, more precious than gold. The analysis of lapis lazuli represented it to be composed of silica, alumina, and soda, 3 colorless bodies, with sulfur and a trace of iron. Nothing could be discovered in it of the nature of a pigment, nothing to which its blue color could be referred, the cause of which was searched for in vain. It might therefore have been supposed that the analyst was here altogether at fault, and that at any rate its artificial production must be impossible. Nevertheless, this has been accomplished, and simply by combining in the proper proportions, as determined by analysis, silica, alumina, soda, iron, and sulfur. Thousands of pounds weight are now manufactured from these ingredients, and this artificial ultramarine is as beautiful as the natural, while for the price of a single ounce of the latter we may obtain many pounds of the former. With the production of artificial lapis lazuli, the formation of mineral bodies by synthesis ceased to be a scientific problem to the chemist. He has no longer sufficient interest in it to pursue the subject. He may now be satisfied that analysis will reveal to him the true constitution of minerals. But to the mineralogist and the geologist it is still in a great measure an unexplored field, offering inquiries of the highest interest and importance to their pursuits. After becoming acquainted with the constituent elements of all the substances within our reach and the mutual relations of these elements, the remarkable transmutation to which the bodies are subject under the influence of vital powers of plants and animals became the principal object of chemical investigations, and the highest point of interest. A new science, inexhaustible as life itself, is here presented us, standing upon the sound and solid foundation of a well-established inorganic chemistry. Thus the progress of science is, like the development of nature's works, gradual and expansive. After the buds and branches spring forth, the leaves and blossoms. After the blossoms, the fruit. Chemistry, in its application to animals and vegetables, endeavors jointly with physiology to enlighten us respecting the mysterious processes and sources of organic life. End of Section 1. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Section 2 of Familiar Letters on Chemistry. This is the LibriVox recording. LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Familiar Letters on Chemistry by Justus Liebig. Letter number 2. My dear Sir, in my former letter, I reminded you that 3 of the supposed elements of the ancients represent the forms or state in which all the ponderable matter of our globe exists. I would now observe that no substance possesses absolutely any one of those conditions, that modern chemistry recognizes nothing unchangeably solid, liquid, or aeriform. Means have been devised for effecting a change of state in almost every known substance. Platinum, alumina, and rock crystal, it is true, cannot be liquefied by the most intense heat of our furnaces, but they melt like wax before the flame of the oxyhydrogen blowpipe. On the other hand, of the 28 gaseous bodies with which we are acquainted, 25 may be reduced to a liquid state, and 1 into a solid. Probably, ere long, similar changes of condition will be extended to every form of matter. There are many things related to this condensation of the gases worthy of your attention. Most aeriform bodies, when subjected to compression, are made to occupy a space which diminishes in the exact ratio of the increase of the compressing force. Very generally, under a force double or triple of the ordinary atmospheric pressure, they become 1/2 or 1/3 of their former volume. This was a long time considered to be a law, and known as the law of Mariotte, but a more accurate study of the subject has demonstrated that this law is by no means of general application. The volume of certain gases does not decrease in the ratio of the increase of the force used to compress them, but in some, a diminution of their bulk takes place in a far greater degree as the pressure increases. Again, if ammoniacal gas is reduced by a compressing force to 1/6 of its volume, or carbonic acid is reduced to 1/36, a portion of them loses entirely the form of a gas and becomes a liquid which, when the pressure is withdrawn, assumes again in an instant its gaseous state. Another deviation from the law of Mariotte. Our process for reducing gases into fluids is of admirable simplicity. A simple bent tube, or a reduction of temperature by artificial means, have superseded the powerful compressing machines of the early experimenters. The cyanuret of mercury, when heated in an open glass tube, is resolved into cyanogen gas and metallic mercury. If this substance is heated in a tube hermetically sealed, the decomposition occurs as before, but the gas, unable to escape and shut up in a space several hundred times smaller than it would occupy as a gas under the ordinary atmospheric pressure, becomes a fluid in that part of the tube which is kept cool. When sulfuric acid is poured upon limestone in an open vessel, carbonic acid escapes with effervescence as a gas, but if the decomposition is effected in a strong, close, and suitable vessel of iron, we obtain the carbonic acid in the state of liquid. In this manner it may be obtained in considerable quantities, even many pounds weight. Carbonic acid is separated from other bodies with which it is combined as a fluid under pressure of 36 atmospheres. The curious properties of fluid carbonic acid are now generally known. When a small quantity is permitted to escape into the atmosphere, it assumes its gaseous state with extraordinary rapidity, and deprives the remaining fluid of caloric so rapidly that it congeals into a white crystalline mass, like snow. At first, indeed, it was thought to be really snow, but upon examination it proved to be pure frozen carbonic acid. This solid, contrary to expectation, exercises only a feeble pressure upon the surrounding medium. The fluid acid enclosed in a glass tube rushes at once, when opened, into a gaseous state, with an explosion which shatters the tube into fragments. But solid carbonic acid can be handled without producing any other effect than a feeling of intense cold. The particles of the carbonic acid being so closely approximated in the solid, the whole force of cohesive attraction (which in the fluid is weak) becomes exerted, and opposes its tendency to assume its gaseous state. But as it receives heat from surrounding bodies, it passes into gas gradually and without violence. The transition of solid carbonic acid into gas deprives all around it of caloric so rapidly and to so great an extent that a degree of cold is produced immeasurably great, the greatest indeed known. 10, 20, or more pounds weight of mercury brought into contact with a mixture of ether and solid carbonic acid becomes in a few moments firm and malleable. This, however, cannot be accomplished without considerable danger. A melancholy accident occurred at Paris, which will probably prevent for the future the formation of solid carbonic acid in these large quantities, and deprive the next generation of the gratification of witnessing these curious experiments. Just before the commencement of the lecture in the laboratory of the Polytechnic School, an iron cylinder, 2 feet and a half long and 1 foot in diameter, in which carbonic acid had been developed for experiment before the class, burst, and its fragments were scattered about with the most tremendous force. It cut off both the legs of the assistant and killed him on the spot. This vessel, formed of the strongest cast iron and shaped like a cannon, had often been employed to exhibit experiments in the presence of the students. You can scarcely think, without shuddering, of the dreadful calamity such an explosion would have occasioned in a hall filled with spectators. When we had ascertained the fact of gases becoming fluid under the influence of cold or pressure, a curious property possessed by charcoal, that of absorbing gas to the extent of many times its volume, 10, 20, or even, as in the case of ammoniacal gas or muriatic acid gas, 80 or 90-fold, which had been long known, no longer remained a mystery. Some gases are absorbed and condensed within the pores of the charcoal into a space several hundred times smaller than they before occupied, and there is now no doubt that they there become fluid or assume a solid state. As in 1,000 other instances, chemical action here supplants mechanical forces. Adhesion or heterogeneous attraction, as it is termed, acquired by this discovery a more extended meaning. It had never before been thought of as a cause of change of state in matter, but it is now evident that a gas adheres to the surface of a solid body by the same force which condenses it into a liquid. The smallest amount of a gas, atmospheric air for instance, can be compressed into a space 1,000 times smaller by mere mechanical pressure, and then its bulk must be to the least measurable surface of a solid body as a grain of sand to a mountain. By the mere effect of mass, the force of gravity, gaseous molecules are attracted by solids and adhere to their surfaces. And when to this physical force is added the feeblest chemical affinity, the liquefiable gases cannot retain their gaseous state. The amount of air condensed by these forces upon a square inch of surface is certainly not measurable. But when a solid body, presenting several hundred square feet of surface within the space of a cubic inch, is brought into a limited volume of gas, we may understand why that volume is diminished, why all gases without exception are absorbed. A cubic inch of charcoal must have, at the lowest computation, a surface of 100 square feet. This property of absorbing gases varies with different kinds of charcoal. It is possessed in a higher degree by those containing the most pores, that is, where the pores are finer, and in a lower degree in the more spongy kinds, that is, where the pores are larger. In this manner, every porous body, rocks, stone, the clods of fields, etc., imbibe air and therefore oxygen. The smallest solid molecule is thus surrounded by its own atmosphere of condensed oxygen. And if in their vicinity other bodies exist which have an affinity for oxygen, a combination is effected. When, for instance, carbon and hydrogen are thus present, they are converted into nourishment for vegetables, into carbonic acid and water. The development of heat when air is imbibed, and the production of steam when the earth is moistened by rain, are acknowledged to be consequences of this condensation by the action of surfaces. But the most remarkable and interesting case of this kind of action is the imbibition of oxygen by metallic platinum. This metal, when massive, is of lustrous white color, but it may be brought, by separating it from its solutions, into so finely divided a state that the particles no longer reflect light, and it forms a powder as black as soot. In this condition, it absorbs 800 times its volume of oxygen gas, and this oxygen must be contained within it in a state of condensation very like that of fluid water. When gases are thus condensed, that is, their particles made to approximate in this extraordinary manner, their properties can be palpably shown. Their chemical actions become apparent as their physical characteristics disappears. The latter consist in the continual tendency of their particles to separate from each other, and it is easy to imagine that this elasticity of gaseous bodies is the principal impediment to the operation of their chemical force, for this becomes more energetic as their particles approximate. In that state in which they exist within the pores or upon the surface of solid bodies, their repulsion ceases, and their whole chemical action is exerted. Thus, combinations which oxygen cannot enter into, decompositions which it cannot effect while in the state of gas, take place with the greatest facility in the pores of platinum containing condensed oxygen. When a jet of hydrogen gas, for instance, is thrown upon spongy platinum, it combines with the oxygen condensed in the interior of the mass. At their point of contact, water is formed, and as the immediate consequence, heat is evolved. The platinum becomes red hot and the gas is inflamed. If we interrupt the current of the gas, the pores of the platinum become instantaneously filled again with oxygen, and the same phenomena can be repeated a second time, and so on interminably. In finely pulverized platinum, and even in spongy platinum, we therefore possess a perpetuum mobile, a mechanism like a watch which runs out and winds itself up, a force which is never exhausted, competent to produce effects of the most powerful kind, and self-renewed ad infinitum. Many phenomena formerly inexplicable are satisfactorily explained by these recently discovered properties of porous bodies. The metamorphosis of alcohol into acetic acid, by the process known as the quick vinegar manufacture, depends upon principles, at a knowledge of which we have arrived by a careful study of these properties. End of section 2, recorded by M.L. Cohen, Cleveland, Ohio, March 2007.
Section 3 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Familiar Letters on Chemistry by Justus Liebig. Letter 3. My dear Sir, the manufacture of soda from common culinary salt may be regarded as the foundation of all our modern improvements in the domestic arts, and we may take it as affording an excellent illustration of the dependence of the various branches of human industry and commerce upon each other, and their relation to chemistry. Soda has been used from time immemorial in the manufacture of soap and glass, two chemical productions which employ and keep in circulation an immense amount of capital. The quantity of soap consumed by a nation would be no inaccurate measure whereby to estimate its wealth and civilization. Of two countries with an equal amount of population, the wealthiest and most highly civilized will consume the greatest weight of soap. This consumption does not subserve sensual gratification, nor depend upon fashion, but upon the feeling of the beauty, comfort, and welfare attendant upon cleanliness; and a regard to this feeling is coincident with wealth and civilization. The rich in the Middle Ages concealed a want of cleanliness in their clothes and persons under a profusion of costly scents and essences, whilst they were more luxurious in eating and drinking, in apparel and horses. With us a want of cleanliness is equivalent to insupportable misery and misfortune. Soap belongs to those manufactured products the money value of which continually disappears from circulation, and requires to be continually renewed. It is one of the few substances which are entirely consumed by use, leaving no product of any worth. Broken glass and bottles are by no means absolutely worthless. For rags we may purchase new cloth, but soap water has no value whatever. It would be interesting to know accurately the amount of capital involved in the manufacture of soap. It is certainly as large as that employed in the coffee trade, with this important difference as respects Germany, that it is entirely derived from our own soil. France formerly imported soda from Spain, Spanish sodas being of the best quality, at an annual expenditure of 20 to 30 millions of francs. During the war with England the price of soda, and consequently of soap and glass, rose continually, and all manufactures suffered in consequence. The present method of making soda from common salt was discovered by Leblanc at the end of the last century. It was a rich boon for France, and became of the highest importance during the wars of Napoleon. In a very short time it was manufactured to an extraordinary extent, especially at the seat of the soap manufactories. Marseilles possessed for a time a monopoly of soda and soap. The policy of Napoleon deprived that city of the advantages derived from this great source of commerce, and thus excited the hostility of the population to his dynasty, which became favourable to the restoration of the Bourbons. A curious result of an improvement in a chemical manufacture. It was not long, however, in reaching England. In order to prepare the soda of commerce, which is the carbonate, from common salt, it is first converted into Glauber's salt, sulphate of soda. For this purpose 80 pounds weight of concentrated sulphuric acid, oil of vitriol, are required to 100 pounds of common salt. The duty upon salt checked for a short time the full advantage of this discovery, but when the government repealed the duty, and its price was reduced to its minimum, the cost of soda depended upon that of sulphuric acid. The demand for sulphuric acid now increased to an immense extent, and to supply it capital was embarked abundantly, as it afforded an excellent remuneration. The origin and formation of sulphuric acid was studied most carefully, and from year to year better, simpler, and cheaper methods of making it were discovered. With every improvement in the mode of manufacture its price fell, and its sale increased in an equal ratio. Sulphuric acid is now manufactured in leaden chambers of such magnitude that they would contain the whole of an ordinary sized house. As regards the process and the apparatus, its manufacture has reached its acme. Scarcely is either susceptible of improvement. The leaden plates of which the chambers are constructed requiring to be joined together with lead, since tin or solder would be acted on by the acid. This process was until lately as expensive as the plates themselves, but now, by means of the oxyhydrogen blowpipe, the plates are cemented together at their edges by mere fusion, without the intervention of any kind of solder. And then as to the process. According to theory, 100 pounds weight of sulphur ought to produce 306 pounds of sulphuric acid. In practice 300 pounds are actually obtained. The amount of loss is therefore too insignificant for consideration. Again, saltpetre being indispensable in making sulphuric acid, the commercial value of that salt had formerly an important influence upon its price. It is true that 100 pounds of saltpetre only are required to 1000 pounds of sulphur, but its cost was 4 times greater than an equal weight of the latter. Travellers had observed near the small seaport of Iquiqui, in the district of Atacama, in Peru, an efflorescence covering the ground over extensive districts. This was found to consist principally of nitrate of soda. Advantage was quickly taken of this discovery. The quantity of this valuable salt proved to be inexhaustible, as it exists in beds extending over more than 200 square miles. It was brought to England at less than half the freight of the East India saltpetre, nitrate of potassa, and as in the chemical manufacture neither the potash nor the soda were required, but only the nitric acid, in combination with the alkali, the soda saltpetre of South America soon supplanted the potash nitre of the East. The manufacture of sulphuric acid received a new impulse. Its price was much diminished without injury to the manufacturer, and, with the exception of fluctuations caused by the impediments thrown in the way of the export of sulphur from Sicily, it soon became reduced to a minimum, and remained stationary. Potash saltpetre is now only employed in the manufacture of gunpowder. It is no longer in demand for other purposes, and thus, if government effect a saving of many £100,000 annually in gunpowder, this economy must be attributed to the increased manufacture of sulphuric acid. We may form an idea of the amount of sulphuric acid consumed when we find that 50,000 pounds weight are made by a small manufactory, and from 200,000 to 600,000 pounds by a large one annually. This manufacture causes immense sums to flow annually into Sicily. It has introduced industry and wealth into the arid and desolate districts of Atacama. It has enabled us to obtain platina from its ores at a moderate and yet remunerating price, since the vats employed for concentrating this acid are constructed of this metal, and cost from £1,000 to £2,000 sterling. It leads to frequent improvements in the manufacture of glass, which continually becomes cheaper and more beautiful. It enables us to return to our fields all their potash, a most valuable and important manure, in the form of ashes, by substituting soda in the manufacture of glass and soap. It is impossible to trace within the compass of a letter all the ramifications of this tissue of changes and improvements resulting from one chemical manufacture, but I must still claim your attention to a few more of its most important and immediate results. I have already told you that in the manufacture of soda from culinary salt it is first converted into sulphate of soda. In this first part of the process the action of sulphuric acid produces muriatic acid to the extent of 1 1/2 the amount of the sulphuric acid employed. At first the profit upon the soda was so great that no one took the trouble to collect the muriatic acid. Indeed, it had no commercial value. A profitable application of it was, however, soon discovered. It is a compound of chlorine, and this substance may be obtained from it purer than from any other source. The bleaching power of chlorine has long been known, but it was only employed upon a large scale after it was obtained from this residuary muriatic acid, and it was found that in combination with lime it could be transported to distances without inconvenience. Thenceforth it was used for bleaching cotton, and but for this new bleaching process it would scarcely have been possible for the cotton manufacture of Great Britain to have attained its present enormous extent. It could not have competed in price with France and Germany. In the old process of bleaching, Every piece must be exposed to the air and light during several weeks in the summer, and kept continually moist by manual labour. For this purpose meadow land, eligibly situated, was essential. Now a single establishment near Glasgow bleaches 1400 pieces of cotton daily throughout the year. What an enormous capital would be required to purchase land for this purpose! How greatly would it increase the cost of bleaching to pay interest upon this capital, or to hire so much land in England! This expense would scarcely have been felt in Germany. Besides the diminished expense, the cotton stuffs bleached with chlorine suffer less in the hands of skilful workmen than those bleached in the sun, and already the peasantry in some parts of Germany have adopted it, and find it advantageous. Another use to which cheap muriatic acid is applied is the manufacture of glue from bones. Bone contains from 30 to 36% of earthy matter, chiefly phosphate of lime, and the remainder is gelatin. When bones are digested in muriatic acid, they become transparent and flexible like leather. The earthy matter is dissolved, and after the acid is all carefully washed away, pieces of glue of the same shape as the bones remain, which are soluble in hot water, and adapted to all the purposes of ordinary glue, without further preparation. Another important application of sulphuric acid may be adduced, namely, to the refining of silver and the separation of gold, which is always present in some proportion in native silver. Silver, as it is usually obtained from mines in Europe, contains in 16 ounces 6 to 8 ounces of copper. When used by the silversmith, or in coining, 16 ounces must contain in Germany 13 ounces of silver, in England about 14½ But this alloy is always made artificially by mixing pure silver with the due proportion of the copper, and for this purpose the silver must be obtained pure by the refiner. This he formerly effected by amalgamation, or by roasting it with lead, and the cost of this process was about £2 for every hundredweight of silver. In the silver so prepared about 1/1200 to 1/2000th part of gold remained. To effect the separation of this by nitro-hydrochloric acid was more expensive than the value of the gold. It was therefore left in utensils, or circulated in coin, valueless. The copper, too, of the native silver was no use whatever; but the 1/1000th part of gold, being about 1½ of the value of the silver, now covers the cost of refining, and affords an adequate profit to the refiner, so that he effects the separation of the copper, and returns to his employer the whole amount of the pure silver, as well as the copper, without demanding any payment. He is amply remunerated by that minute portion of gold. The new process of refining is a most beautiful chemical operation. The granulated metal is boiled in concentrated sulphuric acid, which dissolves both the silver and the copper, leaving the gold nearly pure in the form of a black powder. The solution is then placed in a leaden vessel containing metallic copper. This is gradually dissolved, and the silver precipitated in a pure metallic state. The sulphate of copper thus formed is also a valuable product, being employed in the manufacture of green and blue pigments. Other immediate results of the economical production of sulphuric acid are the general employment of phosphorus matches, and of stearine candles, that beautiful substitute for tallow and wax. 25 years ago the present prices and extensive applications of sulphuric and muriatic acids, of soda, phosphorus, etc., would have been considered utterly impossible. Who is able to foresee what new and unthought of chemical productions, ministering to the service and comforts of mankind, the next 25 years may produce? After these remarks you will perceive that it is no exaggeration to say we may fairly judge of the commercial prosperity of a country from the amount of sulphuric acid it consumes. Reflecting upon the important influence which the price of sulphur exercises upon the cost of production of bleached and printed cotton stuffs, soap, glass, etc., and remembering that Great Britain supplies America, Spain, Portugal, and the East with these, exchanging them for raw cotton, silk, wine, raisins, indigo, etc., etc., we can understand why the English government should have resolved to resort to war with Naples in order to abolish the sulphur monopoly, which the latter power attempted recently to establish. Nothing could be more opposed to the true interests of Sicily than such a monopoly. Indeed, had it been maintained a few years, it is highly probable that sulphur, the source of her wealth, would have been rendered perfectly valueless to her. Science and industry form a power to which it is dangerous to present impediments. It was not difficult to perceive that the issue would be the entire cessation of the exportation of sulphur from Sicily. In the short period the sulphur monopoly lasted, 15 patents were taken out for methods to obtain back the sulphuric acid used in making soda. Admitting that these 15 experiments were not perfectly successful, there can be no doubt it would ere long have been accomplished. But then in gypsum, sulphate of lime, and in heavy spar, sulphate of barytes, we possess mountains of sulphuric acid. In galena, sulphate of lead, and in iron pyrites, we have no less abundance of sulphur. The problem is how to separate the sulphuric acid or the sulphur from these native stores. Hundreds of thousands of pounds weight of sulphuric acid were prepared from iron pyrites, while the high price of sulphur consequent upon the monopoly lasted. We should probably ere long have triumphed over all difficulties and have separated it from gypsum. The impulse has been given, the possibility of the process proved, and it may happen in a few years that the inconsiderate financial speculation of Naples may deprive her of that lucrative commerce. In like manner, Russia, by her prohibitory system, has lost much of her trade in tallow and potash. One country purchases only from absolute necessity from another, which excludes her own productions from her markets. Instead of the tallow and linseed oil of Russia, Great Britain now uses palm oil and coconut oil of other countries. Precisely analogous is the combination of workmen against their employers, which has led to the construction of many admirable machines for superseding manual labour. In commerce and industry, every imprudence carries with it its own punishment. Every oppression immediately and sensibly recoils upon the head of those from whom it emanates. End of section 3. Section 4 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Familiar Letters on Chemistry by Justus Liebig. Letter 4. My dear Sir, one of the most influential causes of improvement in the social condition of mankind is that spirit of enterprise which induces men of capital to adopt and carry out suggestions for the improvement of machinery, the creation of new articles of commerce, or the cheaper production of those already in demand. And we cannot but admire the energy with which such men devote their talents, their time, and their wealth to realize the benefits of the discoveries and inventions of science. For even when these are expended upon objects wholly incapable of realization, nay, even when the idea which first gave the impulse proves in the end to be altogether impracticable or absurd, immediate good to the community generally ensues. Some useful and perhaps unlooked-for result flows directly or springs ultimately from exertions frustrated in their main design. Thus it is also in the pursuit of science. Theories lead to experiments and investigations, and he who investigates will scarcely ever fail of being rewarded by discoveries. It may be, indeed, the theory sought to be established is entirely unfounded in nature, but while searching in a right spirit for one thing, the inquirer may be rewarded by finding others far more valuable than those which he sought. At the present moment electromagnetism, as a moving power, is engaging great attention and study. Wonders are expected from its application to this purpose. According to the sanguine expectations of many persons, it will shortly be employed to put into motion every kind of machinery, and amongst other things it will be applied to impel the carriages of railroads, and this at so small a cost that expense will no longer be matter of consideration. England is to lose her superiority as a manufacturing country, inasmuch as her vast store of coals will no longer avail her as an economical source of motive power. "We," say the German cultivators of this science, "have cheap zinc, and how small a quantity of this metal is required to turn a lathe, and consequently to give motion to any kind of machinery." Such expectations may be very attractive, and yet they are altogether illusory. They will not bear the test of a few simple calculations, and these our friends have not troubled themselves to institute. With a simple flame of spirits of wine, under a proper vessel containing boiling water, a small carriage of 200 to 300 pounds weight can be put into motion, or a weight of 80 to 100 pounds may be raised to a height of 20 feet. The same effects may be produced by dissolving zinc in dilute sulphuric acid in a certain apparatus. This is certainly an astonishing and highly interesting discovery, but the question to be determined is, which of the two processes is the least expensive? In order to answer this question, and to judge correctly of the hopes entertained from this discovery, let me remind you of what chemists denominate equivalents. These are certain unalterable ratios of effects which are proportionate to each other, and may therefore be expressed in numbers. Thus, if we require 8 pounds of oxygen to produce a certain effect, and we wish to employ chlorine for the same effect, we must employ neither more nor less than 35½ pounds weight. In the same manner 6 pounds weight of coal are equivalent to 32 pounds weight of zinc. The numbers representing chemical equivalents express very general ratios of effects, comprehending for all bodies all the actions they are capable of producing. If zinc be combined in a certain manner with another metal, and submitted to the action of dilute sulphuric acid, it is dissolved in the form of an oxide. It is in fact burned at the expense of the oxygen contained in the fluid. A consequence of this action is the production of an electric current, which, if conducted through a wire, renders it magnetic. In thus effecting the solution of a pound weight, for example, of zinc, we obtain a definite amount of force, adequate to raise a given weight 1 inch, and to keep it suspended, and the amount of weight it will be capable of suspending will be the greater the more rapidly the zinc is dissolved. By alternately interrupting and renewing the contact of the zinc with the acid, and by very simple mechanical arrangements, we can give to the iron an upward and downward or a horizontal motion, thus producing the conditions essential to the motion of any machinery. This moving force is produced by the oxidation of the zinc, and setting aside the name given to the force in this case, we know that it can be produced in another manner. If we burn the zinc under the boiler of a steam engine, consequently in the oxygen of the air instead of the galvanic pile, we should produce steam, and by it a certain amount of force. If we should assume, which however is not proved, that the quantity of force is unequal in these cases, that, for instance, we had obtained double or triple the amount in the galvanic pile, or that in this mode of generating force less loss is sustained, we must still recollect the equivalents of zinc and coal, and make these elements of our calculation. According to the experiments of Despretz, 6 pounds weight of zinc, in combining with oxygen, develops no more heat than 1 pound of coal. Consequently, under equal conditions, we can produce 6 times the amount of force with a pound of coal as with a pound of zinc. It is therefore obvious that it would be more advantageous to employ coal instead of zinc, even if the latter produced 4 times as much force in a galvanic pile as an equal weight of coal by its combustion under a boiler. Indeed, it is highly probable that if we burn under the boiler of a steam engine the quantity of coal required for smelting the zinc from its ores, we shall produce far more force than the whole of the zinc so obtained could originate in any form of apparatus whatever. Heat, electricity, and magnetism have a similar relation to each other as the chemical equivalents of coal, zinc, and oxygen. By a certain measure of electricity we produce a corresponding proportion of heat or of magnetic power. We obtain that electricity by chemical affinity, which in one shape produces heat, in another electricity or magnetism. A certain amount of affinity produces an equivalent of electricity in the same manner as, on the other hand, we decompose equivalents of chemical compounds by a definite measure of electricity. The magnetic force of the pile is therefore limited to the extent of the chemical affinity, and in the case before us is obtained by the combination of the zinc and sulphuric acid. In the combustion of coal the heat results from, and is measured by, the affinity of the oxygen of the atmosphere for that substance. It is true that with a very small expense of zinc we can make an iron wire a magnet capable of sustaining 1,000 pounds weight of iron. Let us not allow ourselves to be misled by this. Such a magnet could not raise a single pound weight of iron 2 inches, and therefore could not impart motion. The magnet acts like a rock, which while at rest presses with a weight of 1,000 pounds upon a basis. It is like an enclosed lake, without an outlet and without a fall. But it may be said we have, by mechanical arrangements, given it an outlet and a fall. True, and this must be regarded as a great triumph of mechanics, and I believe it is susceptible of further improvements, by which greater force may be obtained. But with every conceivable advantage of mechanism, no one will dispute that 1 pound of coal, under the boiler of a steam engine, will give motion to a mass several hundred times greater than a pound of zinc in the galvanic pile. Our experience of the employment of electromagnetism as a motory power is, however, too recent to enable us to foresee the ultimate results of contrivances to apply it, and therefore those who have devoted themselves to solve the problem of its application should not be discouraged, inasmuch as it would undoubtedly be a most important achievement to supersede the steam engine, and thus escape the danger of railroads, even at double their expense. Professor Weber of Göttingen has thrown out a suggestion that if a contrivance could be devised to enable us to convert at will the wheels of the steam carriage into magnets, we should be enabled to ascend and descend acclivities with great facility. This notion may ultimately be to a certain extent realized. The employment of the galvanic pile as a motory power, however, must, like every other contrivance, depend upon the question of its relative economy. Probably some time hence it may so far succeed as to be adopted in certain favourable localities. It may stand in the same relation to steam power as the manufacture of beet sugar bears to that of cane, or as the production of gas from oils and resins to that from mineral coal. The history of beet root sugar affords us an excellent illustration of the effect of prices upon commercial productions. This branch of industry seems at length, as to its processes, to be perfected. The most beautiful white sugar is now manufactured from the beet root, in the place of the treacle-like sugar, having the taste of the root, which was first obtained, and instead of 3 or 4%, the proportion obtained by a card, double or even treble that amount is now produced, and, notwithstanding the perfection of the manufacture, it is probable it will ere long be in most places entirely discontinued. In the years 1824 to 1827 the prices of agricultural produce were much lower than at present, while the price of sugar was the same. At that time 1 malter of wheat was 10 shillings, and 1 klafter of wood 18 shillings, and land was falling in price. Reader's note: a malter was a measure containing several bushels, but varying in different countries, and a klafter was a cord, a stack, measuring 6 feet every way. End note. Thus food and fuel were cheap, and the demand for sugar unlimited. It was therefore advantageous to grow beet root, and to dispose of the produce of land as sugar. All these circumstances are now different. A malter of wheat costs 18 shillings, a klafter of wood 30 shillings to 36 shillings. Wages have risen, but not in proportion, while the price of colonial sugar has fallen. Within the limits of the German Commercial League, as for instance at Frankfort on the Main, a pound of the whitest and best loaf sugar is 7d. The import duty is 3d halfpenny, or 30 shillings per hundredweight, leaving 3d halfpenny as the price of the sugar. In the year 1827, then, 1 malter of wheat was equal to 40 pounds weight of sugar, whilst at present that quantity of wheat is worth 70 pounds of sugar. If indeed fuel were the same in price as formerly, and 70 pounds of sugar could be obtained from the same quantity of the root as then yielded 40 pounds, it might still be advantageously produced; but the amount, if now obtained by the most approved methods of extraction, falls far short of this; and as fuel is double the price, and labour dearer, it follows that at present it is far more advantageous to cultivate wheat and to purchase sugar. There are, however, other elements which must enter into our calculations, but these serve to confirm our conclusion that the manufacture of beet root sugar, as a commercial speculation, must cease. The leaves and residue of the root, after the juice was expressed, were used as food for cattle, and their value naturally increased with the price of grain. By the process formerly pursued, 75 pounds weight of juice were obtained from 100 pounds of beet root, and gave 5 pounds of sugar. The method of Schutzenbach, which was eagerly adopted by the manufacturers, produced from the same quantity of root 8 pounds of sugar, but it was attended with more expense to produce, and the loss of the residue as food for cattle. The increased expense in this process arises from the larger quantity of fuel required to evaporate the water; for instead of merely evaporating the juice, the dry residue is treated with water, and we require fuel sufficient to evaporate 106 pounds of fluid instead of 75 pounds, and the residue is only fit for manure. The additional 3 pounds of sugar are purchased at the expense of much fuel and the loss of the residue as an article of food. If the valley of the Rhine possessed mines of diamonds as rich as those of Golconda, Visiapur, or the Brazils, they would probably not be worth the working. At those places the cost of extraction is 28s. to 30s. the carat. With us it amounts to 3 or 4 times as much, to more in fact, than diamonds are worth in the market. The sand of the Rhine contains gold, and in the Grand Duchy of Baden many persons are occupied in gold washing when wages are low; but as soon as they rise this employment ceases. The manufacture of sugar from beet root in the like manner 12 to 14 years ago offered advantages which are now lost. Instead, therefore, of maintaining it at a great sacrifice, it would be more reasonable, more in accordance with true natural economy, to cultivate other and more valuable productions, and with them purchase sugar. Not only would the state be the gainer, but every member of the community. This argument does not apply perhaps to France and Bohemia, where the prices of fuel and of colonial sugar are very different to those in Germany. The manufacture of gas for lighting from coal, resin, and oils stands with us on the same barren ground. The price of the materials from which gas is manufactured in England bears a direct proportion to the price of corn. There the cost of tallow and oil is twice as great as in Germany, but iron and coal are 2/3 cheaper; and even in England the manufacture of gas is only advantageous when the other products of the distillation of coal, the coke, etc., can be sold. It would certainly be esteemed one of the greatest discoveries of the age if any one could succeed in condensing coal gas into a white, dry, solid, odourless substance, portable and capable of being placed upon a candlestick or burned in a lamp. Wax, tallow, and oil are combustible gases in a solid or fluid form, which offer many advantages for lighting not possessed by gas. They furnish, in well constructed lamps, as much light, without requiring the expensive apparatus necessary for the combustion of gas, and they are generally more economical. In large towns, or such establishments as hotels, where coke is in demand, and where losses in stolen tallow or oil must be considered, together with the labour of snuffing candles and cleaning lamps, the higher price of gas is compensated. In places where gas can be manufactured from resin, oil of turpentine, and other cheap oils, as at Frankfort, this is advantageous so long as it is pursued on small scale only. If large towns were lighted in the same manner, the materials would rise in price. The whole amount at present produced would scarcely suffice for 2 such towns as Berlin and Munich. but no just calculation can be made from the present prices of turpentine, resin, etc., which are not produced upon any large scale. End of section 4. Section 5 of Familiar Letters on Chemistry. This is a LibriVox recording. All the LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Familiar Letters on Chemistry by Justus Liebig. Letter 5. My dear Sir, until very recently it was supposed that the physical qualities of bodies, i.e. hardness, colour, density, transparency, etc., and still more their chemical properties, must depend upon the nature of their elements, or upon their composition. It was tacitly received as a principle that two bodies containing the same elements in the same proportion must of necessity possess the same properties. We could not imagine an exact identity of composition giving rise to two bodies entirely different in their sensible appearance and chemical relations. The most ingenious philosophers entertained the opinion that chemical combination is an interpenetration of the particles of different kinds of matter, and that all matter is susceptible of infinite division. This has proved to be altogether a mistake. If matter were infinitely divisible in this sense, its particles must be imponderable, and 1,000,000 of such molecules could not weigh more than an infinitely small one. But the particles of that imponderable matter, which, striking upon the retina, give us the sensation of light, are not, in a mathematical sense, infinitely small. Interpenetration of elements, in the production of a chemical compound, supposes two distinct bodies, A and B, to occupy one and the same space at the same time. If this were so, different properties could not consist with an equal and identical composition. That hypothesis, however, has shared the fate of innumerable imaginative explanations of natural phenomena in which our predecessors indulged. They have now no advocate. The force of truth dependent upon observation is irresistible. A great many substances have been discovered amongst organic bodies composed of the same elements in the same relative proportions, and yet exhibiting physical and chemical properties perfectly distinct one from another. To such substances the term isomeric, from iso, equal, and meros, part, is applied. A great class of bodies known as the volatile oils, oil of turpentine, essence of lemons, oil of balsam, of copaiba, oil of rosemary, oil of juniper, and many others, differing widely from each other in their odour, in their medicinal effects, in their boiling point, in their specific gravity, etc., are exactly identical in composition. They contain the same elements, carbon and hydrogen, in the same proportions. How admirably simple does the chemistry of organic nature present itself to us from this point of view! An extraordinary variety of compound bodies produced with equal weights of two elements, and how wide their dissimilarity! The crystallized part of the oil of roses, the delicious fragrance of which is so well known, a solid at ordinary temperatures, although readily volatile, is a compound body containing exactly the same elements, and in the same proportions, as the gas we employ for lighting our streets; and, in short, the same elements in the same relative quantities are found in a dozen other compounds, all differing essentially in their physical and chemical properties. These remarkable truths, so highly important in their applications, were not received and admitted as sufficiently established without abundant proofs. Many examples have long been known where the analysis of two different bodies gave the same composition, but such cases were regarded as doubtful. At any rate, they were isolated observations, homeless in the realms of science, until at length examples were discovered of two or more bodies whose absolute identity of composition, with totally distinct properties, could be demonstrated in a more obvious and conclusive manner than by mere analysis. That is, they can be converted and reconverted into each other without addition and without subtraction. In cyanuric acid, hydrated cyanic acid, and cyamelide, we have three such isomeric compounds. Cyanuric acid is crystalline, soluble in water, and capable of forming salts with metallic oxides. Hydrated cyanic acid is a volatile and highly blistering fluid, which cannot be brought into contact with water without being instantaneously decomposed. Cyamelide is a white substance very like porcelain, absolutely insoluble in water. Now, if we place the first, cyanuric acid, in a vessel hermetically sealed, and apply a high degree of heat, it is converted by its influence into hydrated cyanic acid, and then, if this is kept for some time at the common temperature, it passes into cyamelide, no other element being present. And again, inversely, cyamelide can be converted into cyanuric acid and hydrated cyanic acid. We have three other bodies which pass through similar changes, in aldehyde, metaldehyde, and etaldehyde, and again, too, in urea and cyanuret of ammonia. Further, 100 parts of aldehyde hydrated butyric acid and acetic ether contain the same elements in the same proportion. Thus one substance may be converted into another without addition or subtraction, and without the participation of any foreign bodies in the change. The doctrine that matter is not infinitely divisible, but on the contrary consists of atoms incapable of further division, alone furnishes us with a satisfactory explanation of these phenomena. In chemical combinations the ultimate atoms of bodies do not penetrate each other, they are only arranged side by side in a certain order, and the properties of the compound depend entirely upon this order. If they are made to change their place, their mode of arrangement, by an impulse from without, they combine again in a different manner, and another compound is formed with totally different properties. We may suppose that one atom combines with one atom of another element to form a compound atom, while in other bodies 2 and 2, 4 and 4, 8 and 8 are united, so that in all such compounds the amount per cent of the elements is absolutely equal, and yet their physical and chemical properties must be totally different, the constitution of each atom being peculiar, in one body consisting of 2, in another of 4, in a third of 8, and in a fourth of 16 simple atoms. The discovery of these facts immediately led to many most beautiful and interesting results. They furnished us with a satisfactory explanation of observations which were before veiled in mystery, a key to many of nature's most curious recesses. Again, solid bodies, whether simple or compound, are capable of existing in two states, which are known by the terms amorphous and crystalline. When matter is passing from a gaseous or liquid state slowly into a solid, an incessant motion is observed, as if the molecules were minute magnets. They are seen to repel each other in one direction, and to attract and cohere together in another, and in the end become arranged into a regular form, which under equal circumstances is always the same for any given kind of matter, that is, crystals are formed. Time and the freedom of motion for the particles of bodies are necessary to the formation of crystals. If we force a fluid or a gas to become suddenly solid, leaving no time for its particles to arrange themselves, and to cohere in that direction in which the cohesive attraction is strongest, no crystals will be formed, but the resulting solid will have a different colour, a different degree of hardness and cohesion, and will refract light differently. In one word, will be amorphous. Thus we have cinnabar as a red and a jet black substance, sulphur, a fixed and brittle body and soft, semi-transparent and ductile, glass as a milk-white opaque substance, so hard that it strikes fire with steel, and in its ordinary and well-known state. These dissimilar states and properties of the same body are occasioned in one case by a regular, in the other by an irregular arrangement of its atoms. One is crystalline, the other amorphous. Applying these facts to natural productions, We have reason to believe that clay slate and many kinds of grey whack are amorphous feldspar, as transition limestone is amorphous marble, basalt and lava mixtures of amorphous zeolite and augite. Anything that influences the cohesion must also in a certain degree alter the properties of bodies. Carbonate of lime, if crystallized at ordinary temperatures, possesses the crystalline form, hardness, and refracting power of common spar. If crystallized at a higher temperature, it has the form and properties of aragonite. Finally, isomorphism, or the equality of form of many chemical compounds having a different composition, tends to prove that matter consists of atoms, the mere arrangement of which produces all the properties of bodies. But when we find that a different arrangement of the same elements gives rise to various physical and chemical properties, and a similar arrangement of different elements produces properties very much the same, may we not inquire whether some of those bodies which we regard as elements may not be merely modifications of the same substance, whether they are not the same matter in a different state of arrangement? We know in fact the existence of iron in two states so dissimilar that in the one it is to the electric chain like platinum, and in the other it is like zinc, so that powerful galvanic machines have been constructed of this one metal. Among the elements are several instances of remarkable similarity of properties. Thus there is a strong resemblance between platinum and iridium, bromine and iodine, iron, manganese and magnesium, cobalt and nickel, phosphorus and arsenic. But this resemblance consists mainly in their forming isomorphous compounds, in which these elements exist in the same relative proportion. These compounds are similar because the atoms of which they are composed are arranged in the same manner. The converse of this is also true. Nitrate of strontia becomes quite dissimilar to its common state if a certain proportion of water is taken into its composition. If we suppose selenium to be merely modified sulphur, and phosphorus modified arsenic, how does it happen, we must inquire, that sulphuric acid and selenic acid, phosphoric and arsenic acid, respectively form compounds which it is impossible to distinguish by their form and solubility? Were these merely isomeric, they ought to exhibit properties quite dissimilar. We have not, I believe, at present the remotest ground to suppose that any one of those substances which chemists regard as elements can be converted into another. Such a conversion, indeed, would presuppose that the element was composed of two or more ingredients, and was in fact not an element. And until the decomposition of these bodies is accomplished, and their constituents discovered, all pretensions to such conversions deserve no notice. Dr. Brown of Edinburgh thought he had converted iron into rhodium, and carbon or paracyanogen into silicon. His paper upon this subject was published in the Transactions of the Royal Society of Edinburgh, and contained internal evidence, without a repetition of his experiments, that he was totally unacquainted with the principles of chemical analysis. But his experiments have been carefully repeated by qualified persons, and they have completely proved his ignorance. His rhodium is iron, and his silicon an impure, incombustible coal. End of section 5.
Letter 6 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Familiar Letters on Chemistry and its relation to Commerce, Physiology, and Agriculture by Justus LIEBIG, M.D., Ph.D., F.R.S., Professor of Chemistry in the University of Gießen. Edited by John Gardner, M.D. Letter 6. My dear Sir, one of the most remarkable effects of the recent progress of science is the alliance of chemistry with physiology, by which a new and unexpected light has been thrown upon the vital processes of plants and animals. We have no longer any difficulty in understanding the different actions of aliments, poisons, and remedial agents. We have a clear conception of the causes of hunger, of the exact nature of death, and we are not, as formerly, obliged to content ourselves with a mere description of their symptoms. It is now ascertained with positive certainty that all the substances which constitute the food of man must be divided into two great classes, one of which serves for the nutrition and reproduction of the animal body, whilst the other ministers to quite different purposes. Thus starch, gum, sugar, beer, wine, spirits, etc., furnish no element capable of entering into the composition of blood, muscular fibre, or any part which is the seat of the vital principle. It must surely be universally interesting to trace the great change our views have undergone upon these subjects, as well as to become acquainted with the researches from which our present knowledge is derived. The primary conditions of the maintenance of animal life are a constant supply of certain matters, animal food, and of oxygen in the shape of atmospheric air. During every moment of life, oxygen is absorbed from the atmosphere in the organs of respiration, and the act of breathing cannot cease while life continues. The observations of physiologists have demonstrated that the body of an adult man, supplied abundantly with food, neither increases nor diminishes in weight during 24 hours, and yet the quantity of oxygen absorbed into his system in that period is very considerable. According to the experiments of Lavoisier, an adult man takes into his system from the atmosphere, in 1 year, no less than 746 pounds weight of oxygen. The calculations of Menzies make the quantity amount even to 837 pounds, but we find his weight at the end of the year either exactly the same or different one way or the other by at most a few pounds. What, it may be asked, has become of the enormous amount of oxygen thus introduced into the human system in the course of 1 year? We can answer this question satisfactorily. No part of the oxygen remains in the body, but is given out again, combined with carbon and hydrogen. The carbon and hydrogen of certain parts of the animal body combine with the oxygen introduced through the lungs and skin, and pass off in the forms of carbonic acid and vapor of water. At every expiration and every moment of life, a certain amount of its elements are separated from the animal organism, having entered into combination with the oxygen of the atmosphere. In order to obtain a basis for the approximate calculation, we may assume, with Lavoisier and Séguin, that an adult man absorbs into his system 32½ ounces of oxygen daily, that is, 46,037 cubic inches, equal to 15,661 grains, French weight, and further, that the weight of the whole mass of his blood is 24 pounds, of which 80% is water. Now, from the known composition of the blood, we know that in order to convert its whole amount of carbon and hydrogen into carbonic acid and water, 64.102 grains of oxygen are required. This quantity will be taken into the system in 4 days and 5 hours. Whether the oxygen enters into combination directly with the elements of the blood, or with the carbon and hydrogen of other parts of the body, it follows inevitably, the weight of the body remaining unchanged and in a normal condition, that as much of these elements as will suffice to supply 24 pounds of blood must be taken into the system in 4 days and 5 hours, and this necessary amount is furnished by the food. We have not, however, remained satisfied with mere approximation. We have determined accurately, in certain cases, the quantity of carbon taken daily in the food, and of that which passes out of the body in the feces and urine combined, that is, uncombined with oxygen. And from these investigations, it appears that an adult man taking moderate exercise consumes 13.9 ounces of carbon, which pass off through the skin and lungs as carbonic acid gas. Footnote 1. This account is deduced from observations made upon the average daily consumption of about 30 soldiers in barracks. The food of these men, consisting of meat, bread, potatoes, lentils, peas, beans, butter, salt, pepper, etc., was accurately weighed during a month, and each article subjected to ultimate analysis. Of the quantity of food, beer, and spirits taken by the men when out of the barracks, we have a close approximation from the report of the sergeant, and from the weight and analysis of the feces and urine, it appears that the carbon which passes off through these channels may be considered equivalent to the amount taken in that portion of the food, and of sauerkraut, which was not included in the estimate. It requires 37 ounces of oxygen to convert 13 9/10 of carbon into carbonic acid. Again, according to the analysis of Boussingault, a horse consumes 79 1/10 ounces of carbon in 24 hours, a milk cow 70 3/4 ounces, so that the horse requires 13 pounds 3 1/2 ounces, and the cow 11 pounds 10 3/4 ounces of oxygen. Footnote 2: 17.5 ounces equals 0.5 kilogram. As no part of the oxygen taken into the system of an animal is given off in any other form than combined with carbon or hydrogen, and as in normal condition or state of health, the carbon and hydrogen so given off are replaced by those elements in the food, it is evident that the amount of nourishment required by an animal for its support must be in direct ratio with the quantity of oxygen taken into its system. Two animals which in equal times take up by means of the lungs and skin unequal quantities of oxygen consume an amount of food unequal in the same ratio. The consumption of oxygen in a given time may be expressed by the number of respirations. It is therefore obvious that in the same animal the quantity of nourishment required must vary with the force and number of respirations. A child breathes quicker than an adult, and consequently requires food more frequently and proportionably in larger quantity, and bears hunger less easily. A bird deprived of food dies on the third day, while a serpent, confined under a bell, respires so slowly that the quantity of carbonic acid generated in an hour can scarcely be observed, and it will live 3 months or longer without food. The number of respirations is fewer in a state of rest than during labor or exercise. The quantity of food necessary in both cases must be in the same ratio. An excess of food, a want of due amount of respired oxygen or of exercise, as also great exercise, which obliges us to take an increased supply of food, together with weak organs of digestion, are incompatible with health. But the quantity of oxygen received by an animal through the lungs not only depends upon the number of respirations, but also upon the temperature of the respired air. The size of the thorax of an animal is unchangeable. We may therefore regard the volume of air which enters at every inspiration as uniform, but its weight, and consequently the amount of oxygen it contains, is not constant. Air is expanded by heat, and contracted by cold. An equal volume of hot and cold air contains, therefore, an unequal amount of oxygen. In summer, atmospheric air contains water in the form of vapor. It is nearly deprived of it in winter. The volume of oxygen in the same volume of air is smaller in summer than in winter. In summer and winter, at the pole and at the equator, we inspire an equal volume of air. The cold air is warmed during respiration and acquires the temperature of the body. In order, therefore, to introduce into the lungs a given amount of oxygen, less expenditure of force is necessary in winter than in summer, and for the same expenditure of force more oxygen is inspired in winter. It is also obvious that in an equal number of respirations we consume more oxygen at the level of the sea than on a mountain. The oxygen taken into the system is given out again in the same form, both in summer and winter. We expire more carbon at a low than at a high temperature, and require more or less carbon in our food in the same proportion. And consequently more is respired in Sweden than in Sicily, and in our own country an eighth more in winter than in summer. Even if an equal weight of food is consumed in hot and cold climates, infinite wisdom has ordained that very unequal proportions of carbon shall be taken in it. The food prepared for the inhabitants of southern climes does not contain in a fresh state more than 12% of carbon, while the blubber and train oil which feed the inhabitants of polar regions contain 66 to 80% of that element. From the same cause, it is comparatively easy to be temperate in warm climates, or to bear hunger for a long time under the equator, but cold and hunger united very soon produce exhaustion. The oxygen of the atmosphere received into the blood in the lungs, and circulated through every part of the animal body, acting upon the elements of food, is the source of animal heat. End of Letter 6.
Section 7 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For information or to volunteer, please visit LibriVox.org. Recording by Gary Gilberd, 2007. Familiar Letters on Chemistry by Justus LIEBIG. Letter 7. My dear Sir, the source of animal heat, its laws, and the influence it exerts upon the functions of the animal body constitute a curious and highly interesting subject, to which I would now direct your attention. All living creatures whose existence depends upon the absorption of oxygen possess within themselves a source of heat, independent of surrounding objects. This general truth applies to all animals, and extends to the seed of plants in the act of germination, to flower buds when developing, and fruits during their maturation. In the animal body, heat is produced only in those parts to which arterial blood, and with it the oxygen absorbed in respiration, is conveyed. Hair, wool, and feathers receive no arterial blood, and therefore in them no heat is developed. The combination of a combustible substance with oxygen is, under all circumstances, the only source of animal heat. In whatever way carbon may combine with oxygen, the act of combination is accomplished by the disengagement of heat. It is indifferent whether this combination takes place rapidly or slowly, at a high or at a low temperature. The amount of heat liberated is a constant quantity. The carbon of the food being converted into carbonic acid within the body must give out exactly as much heat as if it had been directly burnt in oxygen gas or in common air. The only difference is, the production of the heat is diffused over unequal times. In oxygen gas, the combustion of carbon is rapid, and the heat intense. In atmospheric air, it burns slower, and for a longer time, the temperature being lower. In the animal body, the combination is still more gradual, and the heat lower in proportion. It is obvious that the amount of heat liberated must increase or diminish with the quantity of oxygen introduced in equal times by respiration. Those animals, therefore, which respire frequently and consequently consume much oxygen, possess a higher temperature than others which, with a body of equal size to the heat, take into their system less oxygen. The temperature of a child, 102 degrees, is higher than that of an adult, 99 1/2 degrees. That of birds, 104 degrees to 105.4 degrees, is higher than that of quadrupeds, 98 1/2 degrees to 100.4 degrees, or than that of fishes or amphibia, whose proper temperature is from 2.7 to 3.6 degrees higher than that of the medium in which they live. All animals, strictly speaking, are warm-blooded, but in those only which possess lungs is the temperature of the body quite independent of the surrounding medium. The most trustworthy observations prove that, in all climates, in the temperate zones as well as at the equator or the poles, the temperature of the body in man, and in what are commonly called warm-blooded animals, is invariably the same. Yet how different are the circumstances under which they live! The animal body is a heated mass, which bears the same relation to surrounding objects as any other heated mass. It receives heat when the surrounding objects are hotter, it loses heat when they are colder than itself. We know that the rapidity of cooling increases with the difference between the temperature of the heated body and that of the surrounding medium. That is, the colder the surrounding medium, the shorter the time required for the cooling of the heated body. How unequal, then, must be the loss of heat in a man at Palermo, where the external temperature is nearly equal to that of the body, and in the polar regions, where the external temperature is from 70 degrees to 90 degrees lower. Yet, notwithstanding this extremely unequal loss of heat, experience has shown that the blood of the inhabitant of the Arctic Circle has a temperature as high as that of the native of the South, who lives in so different a medium. This fact, when its true significance is perceived, proves that the heat given off to the surrounding medium is restored within the body with great rapidity. This compensation must consequently take place more rapidly in winter than in summer, at the pole than at the equator. Now, in different climates, the quantity of oxygen introduced to the system by respiration, has been already shown, varies according to the temperature of the external air. The quantity of inspired oxygen increases with the loss of heat by external cooling, and the quantity of carbon or hydrogen necessary to combine with this oxygen must be increased in the same ratio. It is evident that the supply of heat lost by cooling is affected by the mutual action of the elements of the food and the inspired oxygen which combine together. To make use of a familiar, but not on that account a less just illustration, the animal body acts in this respect as a furnace, which we supply with fuel. It signifies nothing what intermediate forms food may assume, what changes it may undergo in the body. The last change is uniformly the conversion of its carbon into carbonic acid, and of its hydrogen into water. The unassimilated nitrogen of the food, along with the unburned or unoxidized carbon, is expelled in the urine or in the solid excrements. In order to keep up the furnace at a constant temperature, we must vary the supply of fuel according to the external temperature, that is, according to the supply of oxygen. In the animal body, the food is the fuel. With the proper supply of oxygen, we obtain the heat given out during its oxidation or combustion. In winter, when we take exercise in a cold atmosphere, and when consequently the amount of inspired oxygen increases, the necessity for food containing carbon and hydrogen increases in the same ratio, and by gratifying the appetite thus excited, we obtain the most efficient protection against the most piercing cold. A starving man is soon frozen to death. The animals of prey in those Arctic regions, as every one knows, far exceed in voracity those of the torrid zone. In cold and temperate climates, the air, which incessantly strives to consume the body, urges man to laborious efforts in order to furnish the means of resistance to its action, while in hot climates the necessity of labor to provide food is far less urgent. Our clothing is merely an equivalent for a certain amount of food. The more warmly we are clothed, the less urgent becomes the appetite for food, because the loss of heat by cooling, and consequently the amount of heat to be supplied by food, is diminished. If we were to go naked, like certain savage tribes, or if in hunting or fishing we were exposed to the same degree of cold as the Samoyeds, we would be able with ease to consume 10 pounds of flesh, and perhaps a dozen of tallow candles into the bargain, daily, as warmly clad travellers have related with astonishment of these people. We should then also be able to take the same quantity of brandy or train oil without bad effects, because the carbon and hydrogen of these substances would only suffice to keep up the equilibrium between the external temperature and that of our bodies. According to the preceding expositions, the quantity of food is regulated by the number of respirations, by the temperature of the air, and by the amount of heat given off to the surrounding medium. No isolated fact apparently opposed to this statement can affect the truth of this natural law, without temporary or permanent injury to health. The Neapolitan cannot take more carbon and hydrogen in the shape of food than he expires as carbonic acid and water, and the Esquimaux cannot expire more carbon and hydrogen than he takes into the system as food, unless in a state of disease or of starvation. Let us examine these states a little more closely. The Englishman in Jamaica perceives with regret the disappearance of his appetite, previously a source of frequently recurring enjoyment, and he succeeds, by the use of cayenne pepper and the most powerful stimulants, in enabling himself to take as much food as he was accustomed to eat at home. But the whole of the carbon thus introduced into the system is not consumed. The temperature of the air is too high, and the oppressive heat does not allow him to increase the number of respirations by actual exercise, and thus to proportion the waste to the amount of food taken. Disease of some kind, therefore, ensues. On the other hand, England sends her sick to southern regions, where the amount of oxygen inspired is diminished in a very large proportion. Those whose diseased digestive organs have in a greater or less degree lost the power of bringing the food into the state best adapted for oxidation, and therefore are less able to resist the oxidizing influence of the atmosphere of their native climate, obtain a great improvement in health. The diseased organs of digestion have power to place the diminished amount of food in equilibrium with the inspired oxygen in the mild climate, whilst in a colder region the organs of respiration themselves would have been consumed in furnishing the necessary resistance to the action of atmospheric oxygen. In our climate, hepatic disease, or those arising from excess of carbon, prevail in summer. In winter, pulmonary diseases, or those arising from excess of oxygen, are more frequent. The cooling of the body, by whatever cause it may be produced, increases the amount of food necessary. The mere exposure to the open air, in a carriage, or on the deck of a ship, by increasing radiation and vaporization, increases the loss of heat, and compels us to eat more than usual. The same is true of those who are accustomed to drink large quantities of cold water, which is given off at the temperature of the body, 98½ degrees. It increases the appetite, and persons of weak constitution find it necessary, by continued exercise, to supply to the system the oxygen required to restore the heat abstracted by the cold water. Loud and long continued speaking, the crying of infants, moist air, all exert an decided and appreciable influence on the amount of food which is taken. We have assumed that carbon and hydrogen especially, by combining with oxygen, serve to produce animal heat. In fact, observation proves that hydrogen of the food plays a no less important part than the carbon. The whole process of respiration appears most clearly developed when we consider the state of a man or other animal totally deprived of food. The first effect of starvation is the disappearance of fat, and this fat cannot be traced either in the urine or in the scanty feces. Its carbon and hydrogen have been given off through the skin and lungs in the form of oxidized products. It is obvious that they have served to support respiration. In the case of a starving man, 32½ ounces of oxygen enter the system daily, and are given out again in combination with a part of his body. Curie mentions the case of an individual who was unable to swallow, and whose body lost 100 pounds in weight during a month, and according to Martel, a fat pig overwhelmed in a slip of earth lived 160 days without food, and was found to have diminished in weight, in that time, more than 120 pounds. The whole history of hibernating animals, and the well-established facts of the periodical accumulation in various animals of fat, which at other periods entirely disappears, prove that the oxygen in the respiratory process consumes, without exception, all such substances as are capable of entering into combination with it. It combines with whatever is present to it, and the deficiency of hydrogen is the only reason why carbonic acid is the chief product, for at the temperature of the body the affinity of hydrogen for oxygen far surpasses that of carbon for the same element. We know, in fact, that the grammatrovia expired a volume of carbonic acid equal to that of the oxygen inspired, while the carnivora, the only class of animals whose food contains fat, inspire more oxygen than is equal in volume to the carbonic acid expired. Exact experiments have shown that, in many cases, only half the volume of oxygen is expired in the form of carbonic acid. These observations cannot be gainsaid, and are far more convincing than those arbitrary and artificially produced phenomena, sometimes called experiments, which, made as too often they are, without regard to the necessary and natural conditions, possess no value, and may be entirely dispensed with, especially when, as in the present case, nature affords the opportunity for observation, and when we make a rational use of that opportunity. In the progress of starvation, however, it is not only the fat which disappears, but also, by degrees, all such of the solids as are capable of being dissolved. In the wasted bodies of those who have suffered starvation, the muscles are shrunk and unnaturally soft, and have lost their contractibility. All those parts of the body which are capable of entering into the state of motion have served to protect the remainder of the frame from the destructive influence of the atmosphere. Towards the end, the particles of the brain begin to undergo the process of oxidation, and delirium, mania, and death close the scene. That is to say, all resistance to the oxidizing power of the atmospheric oxygen ceases, and the chemical process of eremacausis, or decay, commences, in which every part of the body, the bones excepted, enters into combination with oxygen. The time which is required to cause death by starvation depends on the amount of fat in the body, on the degree of exercise, as in labour or exertion of any kind, on the temperature of the air, and finally on the presence or absence of water. Through the skin and lungs there escapes a certain quantity of water, and as the presence of water is essential to the continuance of the vital motions, its dissipation hastens death. Cases have occurred in which, a full supply of water being accessible to the sufferer, death has not occurred until after the lapse of 20 days. In one case, life was sustained in this way for the period of 60 days. In all chronic diseases, death is produced by the same cause, namely, the chemical action of the atmosphere. When those substances are wanting, whose function in the organism is to support the process of respiration, when the diseased organs are incapable of performing their proper function of producing these substances, when they have lost the power of transforming the food into that shape in which it may, by entering into combination with the oxygen of the air, protect the system from its influence, then the substance of the organs themselves, the fat of the body, the substance of the muscles, the nerves, and the brain, are unavoidably consumed. The true cause of death in these cases is the respiratory process, that is, the action of the atmosphere. A deficiency of food and a want of power to convert the food into a part of the organism are both equally a want of resistance, and this is the negative cause of the cessation of the vital processes. The flame is extinguished because the oil is consumed, and it is the oxygen of the air which has consumed it. In many diseases, substances are produced which are incapable of assimilation. By the mere deprivation of food, these substances are removed from the body without leaving a trace behind. Their elements have entered into combination with the oxygen of the air. From the first moment that the function of the lungs or of the skin is interrupted or disturbed, compounds rich in carbon appear in the urine, which acquires a brown color. Over the whole surface of the body, oxygen is absorbed and combines with all the substances which offer no resistance to it. In those parts of the body where the access of oxygen is impeded, for example, in the armpits or in the soles of the feet, peculiar compounds are given out, recognizable by their appearance or by their odor. These compounds contain much carbon. Respiration is the falling weight and the bent spring which keeps the clock in motion, and the inspirations and expirations are the strokes of the pendulum which regulate it. In our ordinary timepieces, we know with mathematical accuracy the effect produced on their rate of going by changes in the length of the pendulum or in the external temperature. Few, however, have a clearer conception of the influence of air and temperature on the health of the human body, and yet the research into the conditions necessary to keep it in the normal state is not more difficult than in the case of a clock. End of letter 7.
Letter 8 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Familiar Letters on Chemistry by Justus Liebig. Letter 8. My dear Sir, having attempted in my last letter to explain to you the simple and admirable office subserved by the oxygen of the atmosphere in its combination with carbon in the animal body, I will now proceed to present you with some remarks upon those materials which sustain its mechanisms in motion and keep up their various functions, namely the aliments. If the increase in mass in an animal body, the development and reproduction of its organs depend upon the blood, then those substances only which are capable of being converted into blood can be properly regarded as nourishment. In order then to ascertain what parts of our food are nutritious, we must compare the composition of the blood with the composition of the various articles taken as food. Two substances require especial consideration as the chief ingredients of the blood. One of these separates immediately from the blood when it is withdrawn from the circulation. It is well known that in this case blood coagulates, and separates into a yellowish liquid, the serum of the blood, and a gelatinous mass which adheres to a rod or stick in soft, elastic fibers, when coagulating blood is briskly stirred. This is the fibrin of the blood, which is identical in all its properties with muscular fiber, when the latter is purified from all foreign matters. The second principal ingredient of the blood is contained in the serum, and gives to this liquid all the properties of the white of egg, with which it is indeed identical. When heated, it coagulates into a white elastic mass, and the coagulating substance is called albumin. Fibrin and albumin, the chief ingredients of blood, contain in all 7 chemical elements, among which nitrogen, phosphorus, and sulfur are found. They contain also the earth of bones. The serum retains in solution sea salt and other salts of potash and soda, in which the acids are carbonic, phosphoric, and sulfuric acids. The globules of the blood contain fibrin and albumin, along with a red coloring matter, in which iron is a constant element. Besides these, the blood contains certain fatty bodies in small quantity, which differ from ordinary fats in several of their properties. Chemical analysis has led to the remarkable result that fibrin and albumin contain the same organic elements united in the same proportion, i.e., that they are isomeric, their chemical composition, the proportion of their ultimate elements, being identical. But the difference of their external properties shows that the particles of which they are composed are arranged in a different order. See letter 5. This conclusion has lately been beautifully confirmed by a distinguished physiologist, Dennis, who has succeeded in converting fibrin into albumin, that is, in giving it the solubility and coagulability by heat which characterize the white of egg. Fibrin and albumin, besides having the same composition, agree also in this, that both dissolve in concentrated muriatic acid, yielding a solution of an intense purple color. This solution, whether made with fibrin or albumin, has the very same reactions with all substances yet tried. Both albumin and fibrin, in the process of nutrition, are capable of being converted into muscular fiber, and muscular fiber is capable of being reconverted into blood. These facts have long been established by physiologists, and chemistry has merely proved that these metamorphoses can be accomplished under the influence of a certain force, without the aid of a third substance, or of its elements, and without the addition of any foreign element, or the separation of any element previously present in these substances. If we now compare the composition of all organized parts with that of fibrin and albumin, the following relations present themselves. All parts of the animal body which have a decided shape, which form parts of organs, contain nitrogen. No part of an organ which possesses motion and life is destitute of nitrogen. All of them contain likewise carbon and the elements of water, the latter, however, in no case in the proportion to form water. The chief ingredients of the blood contain nearly 17% of nitrogen, and from numerous analyses it appears that no part of an organ contains less than 17% of nitrogen. The most convincing experiments and observations have proved that the animal body is absolutely incapable of producing an elementary body, such as carbon or nitrogen, out of substances which do not contain it, and it obviously follows that all kinds of food fit for the production either of blood or of cellular tissue, membranes, skin, hair, muscular fiber, etc., must contain a certain amount of nitrogen, because that element is essential to the composition of the above-named organs, because the organs cannot create it from the other elements presented to them, and finally, because no nitrogen is absorbed from the atmosphere in the vital process. The substance of the brain and nerves contains a large quantity of albumin, and, in addition to this, two peculiar fatty acids, distinguished from other fats by containing phosphorus, phosphoric acid. One of these contains nitrogen, Fremy. Finally, water and common fat are those ingredients of the body which are destitute of nitrogen. Both are amorphous or unorganized, and only so far take part in the vital process as that their presence is required for the due performance of the vital functions. The inorganic constituents of the body are iron, lime, magnesia, common salt, and the alkalis. The nutritive process is seen in its simplest form in carnivorous animals. This class of animals lives on the blood and flesh of the graminivora, but this blood and flesh are, in all their properties, identical with their own. Neither chemical nor physiological differences can be discovered. The nutriment of carnivorous animals is derived originally from blood. In their stomach it becomes dissolved, and capable of reaching all other parts of the body. In its passage it is again converted into blood, and from this blood are reproduced all those parts of their organization which have undergone change or metamorphosis. With the exception of hooves, hair, feathers, and the earth of bones, every part of the food of carnivorous animals is capable of assimilation. In a chemical sense, therefore, it may be said that a carnivorous animal, in supporting the vital process, consumes itself. That which serves for its nutrition is identical with those parts of its organization which are to be renewed. The process of nutrition in graminivorous animals appears at first sight altogether different. Their digestive organs are less simple, and their food consists of vegetables, the great mass of which contains but little nitrogen. From what substances, it may be asked, is the blood formed, by means of which their organs are developed? This question may be answered with certainty. Chemical researches have shown that all such parts of vegetables as can afford nutriment to animals contain certain constituents which are rich in nitrogen, and the most ordinary experience proves that animals require for their support and nutrition less of these parts of plants in proportion as they abound in the nitrogenized constituents. Animals cannot be fed on matters destitute of these nitrogenized constituents. These important products of vegetation are especially abundant in the seeds of the different kinds of grain, and of peas, beans, and lentils, in the roots and the juices of what are commonly called vegetables. They exist, however, in all plants, without exception, and in every part of plants in larger or smaller quantity. These nitrogenized forms of nutriment in the vegetable kingdom may be reduced to three substances, which are easily distinguished by their external characters. Two of them are soluble in water, the third is insoluble. When the newly expressed juices of vegetables are allowed to stand, a separation takes place in a few minutes. A gelatinous precipitate, commonly of a green tinge, is deposited, and this, when acted on by liquids which remove the coloring matter, leaves a grayish-white substance, well known to druggists as the deposit from vegetable juices. This is one of the nitrogenized compounds which serves for the nutrition of animals, and has been named vegetable fibrin. The juice of grapes is especially rich in this constituent, but it is most abundant in the seeds of wheat, and of the cerealia generally. It may be obtained from wheat flour by a mechanical operation, and in a state of tolerable purity. It is then called gluten. But the glutinous property belongs, not to vegetable fibrin, but to a foreign substance present in small quantity, which is not found in the other cerealia. The method by which it is obtained sufficiently proves that it is insoluble in water, although we cannot doubt that it was originally dissolved in the vegetable juice, from which it afterwards separated, exactly as fibrin does from blood. The second nitrogenized compound remains dissolved in the juice after the separation of the fibrin. It does not separate from the juice at the ordinary temperature, but is instantly coagulated when the liquid containing it is heated to the boiling point. When the clarified juice of nutritious vegetables, such as cauliflower, asparagus, mangel wurzel, or turnips, is made to boil, a coagulum is formed, which it is absolutely impossible to distinguish from the substance which separates as a coagulum when the serum of blood or the white of an egg, diluted with water, are heated to the boiling point. This is vegetable albumin. It is found in the greatest abundance in certain seeds, in nuts, almonds, and others, in which the starch of the gramineae is replaced by oil. The third nitrogenized constituent of the vegetable food of animals is vegetable casein. It is chiefly found in the seeds of peas, beans, lentils, and similar leguminous seeds. Like vegetable albumin, it is soluble in water, but differs from it in this, that its solution is not coagulated by heat. When the solution is heated or evaporated, a skin forms on its surface, and the addition of an acid causes a coagulum, just as in animal milk. These three nitrogenized compounds, vegetable fibrin, albumin, and casein, are the true nitrogenized constituents of the food of graminivorous animals. All other nitrogenized compounds occurring in plants are either rejected by animals, as in the case of the characteristic principles of poisonous and medicinal plants, or else they occur in the food in such very small proportion that they cannot possibly contribute to the increase of mass in the animal body. The chemical analysis of these three substances has led to the very interesting result that they contain the same organic elements, united in the same proportion by weight, and, what is still more remarkable, that they are identical in composition with the chief constituents of blood, animal fibrin, and albumin. They all three dissolve in concentrated muriatic acid with the same deep purple color, and even in their physical characters, animal fibrin and albumin are in no respect different from vegetable fibrin and albumin. It is especially to be noticed that by the phrase identity of composition we do not here intend mere similarity, but that even in regard to the presence and relative amount of sulfur, phosphorus, and phosphate of lime, no difference can be observed. How beautifully and admirably simple, with the aid of these discoveries, appears the process of nutrition in animals, the formation of their organs in which vitality chiefly resides. Those vegetable principles which in animals are used to form blood contain the chief constituents of blood, fibrin and albumin, ready formed, as far as regards their composition. All plants, besides, contain a certain quantity of iron, which reappears in the coloring matter of the blood. Vegetable fibrin and animal fibrin, vegetable albumin and animal albumin, hardly differ, even in form. If these principles be wanting in the food, the nutrition of the animal is arrested, and when they are present, the graminivorous animal obtains in its foods the very same principles on the presence of which the nutrition of the carnivore entirely depends. Vegetables produce in their organism the blood of all animals, for the carnivora, in consuming the blood and flesh of the graminivora, consume, strictly speaking, only the vegetable principles which have served for the nutrition of the latter. Vegetable fibrin and albumin take the form in the stomach of the graminivorous animal as animal fibrin and albumin do in that of the carnivorous animal. From what has been said, it follows that the development of the animal organism and its growth are dependent on the reception of certain principles identical with the chief constituents of blood. In this sense, we may say that the animal organism gives to the blood only its form, that it is incapable of creating blood out of other substances which do not already contain the chief constituents of that fluid. We cannot, indeed, maintain that the animal organism has no power to form other compounds, for we know that it is capable of producing an extensive series of compounds, differing in composition from the chief constituents of blood, but these last, which form the starting point of the series, it cannot produce. The animal organism is a higher kind of vegetable, the development of which begins with those substances with the production of which the life of an ordinary vegetable ends. As soon as the latter has borne seed, it dies, or a period of its life comes to a termination. In that endless series of compounds, which begins with carbonic acid, ammonia, and water, the sources of the nutrition of vegetables, and includes the most complex constituents of the animal brain, there is no blank, no interruption. The first substance capable of affording nutriment to animals is the last product of the creative energy of vegetables. The substance of cellular tissue and of membranes, of the brain and nerves, these the vegetable cannot produce. The seemingly miraculous in the production agency of vegetables disappears in a great degree when we reflect that the production of the constituents of blood cannot appear more surprising than the occurrence of the fat of beef and mutton in cocoa beans, of human fat in olive oil, of the principal ingredient of butter in palm oil, and of horse fat and train oil in certain oily seeds. End of Letter 8.
Section 9 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Familiar Letters on Chemistry, Letter 9. My dear Sir, the facts detailed in my last letter will satisfy you as to the manner in which the increase of mass in an animal, that is, its growth, is accomplished. We still have to consider a most important question, namely, the function performed in the animal system by substances destitute of nitrogen, such as sugar, starch, gum, pectin, etc. The most extensive class of animals, the graminivora, cannot live without these substances. Their food must contain a certain amount of one or more of them, and if these compounds are not supplied, death quickly ensues. This important inquiry extends also to the constituents of the food of carnivorous animals in the earliest periods of life, for this food also contains substances which are not necessary for their support in the adult state. The nutrition of the young of carnivora is obviously accomplished by means similar to those by which the graminivora are nourished. Their development is dependent on the supply of a fluid, which the body of the mother secretes in the shape of milk. Milk contains only one nitrogenized constituent, known under the name of casein. Besides this, its chief ingredients are butter (fat) and sugar of milk. The blood of the young animal, its muscular fiber, cellular tissue, nervous matter, and bones must have derived their origin from the nitrogenized constituent of milk, the casein, for butter and sugar of milk contain no nitrogen. Now, the analysis of casein has led to the result which, after the details I have given, can hardly excite your surprise, that this substance also is identical in composition with the chief constituents of blood, fibrin and albumin. Nay more, a comparison of its properties with those of vegetable casein has shown that these two substances are identical in all their properties, insomuch that certain plants, such as peas, beans, and lentils, are capable of producing the same substance which is formed from the blood of the mother, and employed in yielding the blood of the young animal. The young animal, therefore, receives in the form of casein, which is distinguished from fibrin and albumin by its greater solubility and by not coagulating when heated, the chief constituent of the mother's blood. To convert casein into blood, no foreign substance is required, and in the conversion of the mother's blood into casein, no elements of the constituents of blood have been separated. When chemically examined, casein is found to contain a much larger proportion of the earth of bones than blood does, and that in a very soluble form, capable of reaching every part of the body. Thus, even in the earliest period of its life, the development of the organs in which vitality resides is, in the carnivorous animal, dependent on the supply of a substance, identical in organic composition with the chief constituents of its blood. What, then, is the use of the butter and the sugar of milk? How does it happen that these substances are indispensable to life? Butter and sugar of milk contain no fixed bases, no soda nor potash. Sugar of milk has a composition closely allied to that of the other kinds of sugar, of starch and of gum. All of them contain carbon and the elements of water, the latter precisely in the proportion to form water. There is added, therefore, by means of these compounds, to the nitrogenized constituents of food, a certain amount of carbon, or, as in the case of butter, of carbon and hydrogen, that is, an excess of elements which cannot possibly be employed in the production of blood, because the nitrogenized substances contained in the food already contain exactly the amount of carbon which is required for the production of fibrin and albumin. In the adult carnivorous animal, which neither gains nor loses weight perceptibly from day to day, its nourishment, the waste of organized tissue, and its consumption of oxygen stand to each other in a well-defined and fixed relation. The carbon of the carbonic acid given off with that of the urine, the nitrogen of the urine, and the hydrogen given off as ammonia and water, these elements taken together must be exactly equal in the weight to the carbon, nitrogen, and hydrogen of the metamorphosed tissues, and since these last are exactly replaced by food, to carbon, nitrogen, and hydrogen of the food. Were this not the case, the weight of the animal could not possibly remain unchanged. But in the young of the carnivora, the weight does not remain unchanged. On the contrary, it increases from day to day by an appreciable quantity. This fact presupposes that the assimilative processes in the young animal is more energetic, more intense than the process of transformation in the existing tissues. If both processes were equally active, the weight of the body could not increase, and were the waste by transformation greater, the weight of the body would decrease. Now, the circulation of the young animal is not weaker, but, on the contrary, more rapid. The respirations are more frequent, and for equal bulks, the consumption of oxygen must be greater, rather than smaller, in the young than in the adult animal. But, since the metamorphosis of organized parts goes on more slowly, there would ensue a deficiency of those substances, the carbon and hydrogen which are adapted for a combination with oxygen, because, in the carnivora, nature has destined the new compounds, produced by the metamorphosis of organized parts, to furnish the necessary resistance to the action of the oxygen, and to produce animal heat. What is wanting for these purposes, an infinite wisdom has supplied to the young in its natural food. The carbon and hydrogen of butter, and the carbon of sugar of the milk, no part of either of which can yield blood, fibrin, and albumin, are destined for the support of the respiratory processes, at an age when a greater resistance is opposed to the metamorphosis of existing organisms, or, in other words, to the production of compounds which, in the adult state, are produced in quantity amply sufficient for the purpose of respiration. The young animal receives the constituents of its blood in the casein of the milk. A metamorphosis of existing organs goes on, for bile and urine are secreted. The materials of the metamorphosed parts are given off in the form of urine, of carbonic acid, and of water. But the butter and sugar of milk also disappear. They cannot be detected in the feces. The butter and sugar of milk are given out in the form of carbonic acid and water, and their conversion into oxidized products furnishes the clearest proof that far more oxygen is absorbed than is required to convert the carbon and hydrogen of the metamorphosed tissues into carbonic acid and water. The change and metamorphosis of organized tissues going on in the vital processes in the young animal consequently yield, in a given time, much less carbon and hydrogen in the form adapted for the respiratory processes than correspond to the oxygen taken up in the lungs. The substance and of its organized parts would undergo a more rapid consumption, and would necessarily yield to the action of the oxygen, were not the deficiency of carbon and hydrogen supplied from another source. The continued increase of mass or growth, and the free and unimpeded development of the organs of the young animal, are dependent on the presence of foreign substances, which, in the nutritive process, have no other function than to protect the newly formed organs from the action of the oxygen. The elements of these substances unite with the oxygen. The organs themselves could not do so without being consumed. That is, growth or increase of mass in the body, the consumption of oxygen remaining the same, would be utterly impossible. The preceding considerations leave no doubt as to the purpose for which nature has added to the food of the young of carnivorous mammalia substance devoid of nitrogen, which their organism cannot employ for nutrition, strictly so called, that is, for the production of blood, substances which may be entirely dispensed with in the nourishment in the adult state. In the young of carnivorous birds, the want of all motion is an obvious cause of diminished waste in the organized parts. Hence, milk is not provided for them. The nutritive processes in the carnivora thus presents itself under two distinct forms, one of which we meet again in the graminivora. In the graminivorous animals, we observe that during their whole life their existence depends on a supply of substances having a composition identical with that of sugar of milk, or closely resembling it. Everything that they consume as food contains a certain quantity of starch, gum, or sugar mixed with other matters. The function performed in the vital processes of the graminivora by these substances is indicated in a very clear and convincing manner when we take into consideration the very small relative amount of the carbon which these animals consume in the nitrogenized constituents of their food, which bears no proportion whatever to the oxygen absorbed through the skin and lungs. A horse, for example, can be kept in perfectly good condition if he obtains as food 15 pounds of hay and 4½ pounds of oats daily. If we now calculate the whole amount of nitrogen in these matters, as ascertained by analysis, (1 1/2% in the hay, 2.2% in the oats), in the form of blood, that is, as fibrin and albumin, with the due proportion of water in the blood, (80%), the horse receives daily no more than 4½ ounces of nitrogen, corresponding to about 8 pounds of blood. But along with this nitrogen, that is combined with it in the form of fibrin and albumin, the animal receives only about 14½ ounces of carbon. Without going further into the calculation, it will readily be admitted that the volume of air inspired and expired by a horse, the quantity of oxygen consumed, and, as a necessary consequence, the amount of carbonic acid given out by the animal, are much greater than in the respiratory process in man. But an adult man consumes daily about 14 ounces of carbon, and the determination of Bosengalt, according to which a horse expires 79 ounces daily, cannot be very far from the truth. In the nitrogenized constituents of its food, therefore, the horse receives rather less than the 1/5 part of the carbon which his organism requires for the support of the respiratory process. And we see that the wisdom of the Creator has added to his food the 4/5 which are wanting, in various forms, as starch, sugar, etc., with which the animal must be supplied, or his organism will be destroyed by the action of the oxygen. It is obvious that in the system of the graminivora, whose food contains so small a portion relatively of the constituents of the blood, the process of metamorphosis in existing tissues, and consequently the restoration or reproduction, must go on far less rapidly than in the carnivora. Were this not the case, a vegetation 1,000 times more luxuriant than the actual one would not suffice for their nourishment. Sugar, gum, and starch would no longer be necessary to support life in these animals, because, in that case, the products of the waste or metamorphosis of the organized tissues would contain enough carbon to support the respiratory process. End of section 9, recorded by M.L. Cohen, Cleveland, Ohio, March 2007. Section 10 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Familiar Letters on Chemistry by Justus Liebig, Letter 10. My dear Sir, let me now apply the principles announced in the preceding letters to the circumstances of our own species. Man, when confined to animal food, requires for his support and nourishment extensive sources of food, even more widely extended than the lion and tiger, because, when he has the opportunity, he kills without eating. A nation of hunters, on a limited space, is utterly incapable of increasing its numbers beyond a certain point, which is soon attained. The carbon necessary for respiration must be obtained from the animals, of which only a limited number can live on the space supposed. These animals collect from plants the constituents of their organs and of their blood, and yield them, in turn, to the savages who live by the chase alone. They again receive this food unaccompanied by those compounds destitute of nitrogen, which, during the life of the animals, serve to support the respiratory process. In such men, confined to an animal diet, it is the carbon of the flesh and of the blood which must take the place of starch and sugar. But 15 pounds of flesh contains no more carbon than 4 pounds of starch, and while the savage with one animal and an equal weight of starch should maintain life and health for a certain number of days, he would be compelled, if confined to flesh alone, in order to procure the carbon necessary for respiration, during the same time to consume 5 such animals. It is easy to see from these considerations how close the connection is between agriculture and the multiplication of the human species. The cultivation of our crops has ultimately no other object than the production of a maximum of those substances which are adapted for assimilation and respiration in the smallest possible space. Grain and other nutritious vegetables yield us, not only in starch, sugar, and gum, the carbon which protects our organs from the action of oxygen, and produces in the organism the heat which is essential to life, but also in the form of vegetable fibrin, albumin, and casein, our blood from which the other parts of our body are developed. Man, when confined to animal food, respires like the carnivora at the expense of the matters produced by the metamorphosis of organized tissues, and, just like the lion, tiger, hyena, in the cases of a menagerie, are compelled to accelerate the waste of the organized tissues by incessant motion in order to furnish the matter necessary for respiration, so the savage, for the very same object, is forced to make the most laborious exertions and go through a vast amount of muscular exercise. He is compelled to consume force merely in order to supply matter for respiration. Cultivation is the economy of force. Science teaches us the simplest means of obtaining the greatest effort with the smallest expenditure of power, and with given means to produce a maximum of force. The unprofitable exertion of power, the waste of force in agriculture, in other branches of industry, in science, or in social economy, is characteristic of the savage state, or of the want of knowledge. In accordance with what I have already stated, you will perceive that the substances of which the food of man is composed may be divided into 2 classes, into nitrogenized and non-nitrogenized. The former are capable of conversion into blood, the latter are incapable of this transformation. Out of those substances which are adapted to the formation of blood are formed all the organized tissues. The other class of substances, in the normal state of health, serve to support the process of respiration. The former may be called the plastic elements of nutrition, the latter, elements of respiration. Among the former we reckon vegetable fibrin, vegetable albumin, vegetable casein, animal flesh, animal blood. Among the elements of respiration in our food are fat, pectin, starch, basarine, gum, wine, cane sugar, beer, grape sugar, spirits, sugar of milk. The most recent and exact researches have established as a universal fact, to which nothing yet known is opposed, that nitrogenized constituents of vegetable food have a composition identical with that of the constituents of the blood. No nitrogenized compound, the composition of which differs from that of fibrin, albumin, and casein, is capable of supporting the vital process in animals. The animal organism unquestionably possesses the power of forming, from the constituents of its blood, the substances of its membranes and cellular tissue, of the nerves and brain, and of the organic part of cartilage and bones. but the blood must be supplied to it perfect in everything but its form, that is, in its chemical composition. If this be not done, a period is rapidly put to the formation of blood, and consequently to life. This consideration enables us easily to explain how it happens that the tissues yielding gelatin or chondrine, as for example the gelatine of skin or of bones, are not adapted for the support of the vital process, for their composition is different from that of fibrin or albumin. It is obvious that this means nothing more than that those parts of the animal organism which form the blood do not possess the power of effecting a transformation in the arrangement of the elements of gelatin, or of those tissues which contain it. The gelatinous tissues, the gelatin of the bones, the membranes, the cells of the skin suffer in the animal body, under the influence of oxygen and moisture, a progressive alteration. A part of these tissues is separated, and must be restored from the blood. But this alteration and restoration are obviously confined within very narrow limits. While, in the body of a starving or sick individual, the fat disappears and the muscular tissue takes once more the form of blood, we find that the tendons and membranes retain their natural condition, and the limbs of the dead body their connections, which depend on the gelatinous tissues. On the other hand, we see that the gelatin of bones devoured by a dog entirely disappears, while only the bone earth is found in his excrements. The same is true of man, when fed on food rich in gelatin, as for example strong soup. The gelatin is not to be found either in the urine or in the feces, and consequently must have undergone a change and must have served some purpose in the animal economy. It is clear that the gelatin must be expelled from the body in a form different from that in which it was introduced as food. When we consider the transformation of the albumin of the blood into a part of an organ composed of fibrin, the identity and composition of the two substances renders the change easily conceivable. Indeed, we find the change of a dissolved substance in an insoluble organ of vitality, chemically speaking, natural and easily explained, on account of this very identity of composition. Hence, the opinion is not unworthy of closer investigation, that gelatin, when taken in the dissolved state, is again converted in the body into cellular tissue, membrane, and cartilage, that it may serve for reproduction of such parts of these tissues as have been wasted, and for their growth. And when the powers of nutrition in the whole body are affected by a change of the health, then, even should the power of forming blood remain the same, the organic force by which the constituents of the blood are transformed into cellular tissue and membranes must necessarily be enfeebled by sickness. In the sick man, the intensity of the vital force, its power to produce metamorphoses, must be diminished as well in the stomach as in all other parts of the body. In this condition, the uniform experience of practical physicians shows that gelatinous matters in a dissolved state exercise a most decided influence on the state of the health. Given in a form adapted for assimilation, they serve to husband the vital force, just as may be done, in the case of the stomach, by due preparation of the food in general. Brittleness in the bones of graminivorous animals is clearly owing to a weakness in those parts of the organism whose function it is to convert the constituents of the blood into cellular tissue and membrane. And if we can trust to the reports of the physicians who have resided in the East, the Turkish women, in their diet of rice and in the frequent use of enemata of strong soup, have united the conditions necessary for the formation both of cellular tissue and of fat. End of section 10. Recording by M.L. Cohen, Cleveland, Ohio, March 2007.
Section 11 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larysa Jaworski, Brisbane, Australia, March 2007. Familiar Letters on Chemistry by Justus LIEBIG. Letter 11. My dear Sir, In the immense yet limited expanse of the ocean, the animal and vegetable kingdoms are mutually dependent upon and successive to each other. The animals obtain their constituent elements from the plants and restore them to the water in their original form when they are again serve as nourishment to a new generation of plants. The oxygen which marine animals withdraw in their respiration from the air, dissolved in sea water which is returned to the water by the vital processes of sea plants, that air is richer in oxygen than atmospheric air, containing 32 to 33%. Oxygen also combines with the products of the putrefaction of dead animal bodies, changes their carbon into carbonic acid, their hydrogen into water, and their nitrogen assumes again the form of ammonia. Thus we observe in the ocean a circulation takes place without the addition or subtraction of any element, unlimited in duration, although limited in extent, inasmuch as in a confined space the nourishment of plants exists in a limited quantity. We well know that marine plants cannot derive a supply of humus for their nourishment through their roots. Look at the great sea tang, the Fucus giganteus. This plant, according to Cook, reaches a height of 360 feet, and a single specimen with its immense ramifications nourishes thousands of marine animals. Yet its root is a small body no larger than a fist. What nourishment can this draw from a naked rock, upon the surface of which there is no perceptible change? It is quite obvious that these plants require only a hold, a fastening to prevent a change of place, as a counterpoise to their specific gravity, which is less than that of the medium in which they float. That medium provides the necessary nourishment and presents it to the surface of every part of the plant. Sea water contains not only carbonic acid and ammonia, but the alkaline and earthy phosphates and carbonates required by these plants for their growth, and which we always find as a constant constituent of their ashes. All experience demonstrates that the conditions of the existence of marine plants are the same which are essential to terrestrial plants, but the latter do not live like sea plants, in a medium which contains all their elements and surrounds with appropriate nourishment every part of their organs. On the contrary, they require two media, one of which, namely the soil, contains those elements which are absent from the medium surrounding them, i.e. the atmosphere. Is it possible that we could ever be in doubt respecting the office which the soil and its component parts subserve in the existence and growth of vegetables, that there should have been a time when the mineral elements of plants were not regarded as absolutely essential to their vitality? Has not the same circulation been observed on the surface of the earth which we have just contemplated in the ocean, the same incessant change, disturbance, and restitution of equilibrium? Experience in agriculture shows that the production of vegetables on a given surface increases with the supply of certain matters, originally parts of the soil which had been taken up from it by plants, the excrements of man and animals. These are nothing more than matters derived from vegetable food, which, in the vital processes of animals, or after their death, assumes again the form under which they originally existed, as parts of the soil. Now we know that the atmosphere contains none of these substances, and therefore can replace none, and we know that their removal from a soil destroys its fertility, which may be restored and increased by a new supply. It is possible, after so many decisive investigations into the origin of the elements of animals and vegetables, to the use of alkalis, of lime, and the phosphates, any doubt can exist as to the principles upon which a rational agriculture depends. Can the art of agriculture be based upon anything but the restitution of a disturbed equilibrium? Can it be imagined that any country, however rich and fertile, with a flourishing commerce, which for centuries exports its produce in the shape of grain and cattle, will maintain its fertility, if the same commerce does not restore in some form of manure those elements which have been removed from the soil, and which cannot be replaced by the atmosphere? Must not the same fate await every such country which has actually befallen the once prolific soil of Virginia, now in many parts no longer able to grow its former staple productions, wheat and tobacco? In the large towns of England, the produce both of English and foreign agriculture is largely consumed. Elements of the soil indispensable to plants do not return to the fields. Contrivances resulting from the manners and custom of the English people, and peculiar to them, render it difficult, perhaps impossible, to collect the enormous quantity of phosphates which are daily, as solid and liquid excrements, carried into the rivers. These phosphates, although present in the soil in the smallest quantity, are its most important mineral constituents. It was observed that many English fields exhausted in that manner immediately doubled their produce, as if by miracle, when dressed with bone earth imported from the continent. But if the export of bones from Germany is continued to the extent it has hitherto reached, our soil must be gradually exhausted, and the extent of our loss may be estimated by considering that 1 pound of bones contains as much phosphoric acid as 100 weight of grain. The imperfect knowledge of nature and the properties and relations of matter possessed by the alchemists gave rise, in their time, to an opinion that metals as well as plants could be produced from a seed. The regular forms and ramifications seen in crystals they imagined to be the leaves and branches of metal plants, and as they saw the seeds of plants grow, producing root, stem, and leaves, and again blossoms, fruit, and seed, apparently without receiving any supply of appropriate material, they deemed it worthy of zealous inquiry to discover the seed of gold, and the earth necessary for its development. If the metal seeds were once obtained, might not they entertain hopes of their growth? Such ideas could only be entertained when nothing was known of the atmosphere and its participation with the earth in administering to the vital processes of plants and animals. Modern chemistry indeed produces the elements of water, and combining them forms water anew. But it does not create those elements, it derives them from water. The new formed artificial water has been water before. Many of our farmers are like the alchemists of old. They are searching for the miraculous seed, the means which, without any further supply of nourishment to a soil scarcely rich enough to be sprinkled with indigenous plants, shall produce crops of grain 100-fold. The experience of centuries, nay thousands of years, is insufficient to guard men against these fallacies. Our only security from these and similar absurdities must be derived from a correct knowledge of scientific principles. In the first period of natural philosophy, organic life was supposed to be derived from water only. Afterwards it was admitted that certain elements derived from the air must be superadded to the water. But we now know that other elements must be supplied by the earth if plants are to thrive and multiply. The amount of materials contained in the atmosphere suited to the nourishment of plants is limited, but it must be abundantly sufficient to cover the whole surface of the earth with a rich vegetation. Under the tropics, and in those parts of our globe where the most genial conditions of fertility exist, a suitable soil, a moist atmosphere, and high temperature, vegetation is scarcely limited by space, and where the soil is wanting it is gradually supplied by the decaying leaves, bark, and branches of plants. It is obvious there is no deficiency of atmospheric nourishment for plants in those regions, nor are these wanting in our own cultivated fields. All that plants require for their development is conveyed to them by the incessant motions of the atmosphere. The air between the tropics contains no more than that of the Arctic zones, and yet how different is the amount of produce and equal surface of land in the two situations. This is easily explicable. All the plants of tropical climes, the oil and wax palms, the sugar cane, etc., contain only a small quantity of the elements of the blood necessary to the nutrition of animals, as compared with our cultivated plants. The tubers of the potato in Chile, its native country, where the plant resembles a shrub, if collected from an acre of land, would scarcely suffice to maintain an Irish family for a single day. Darwin. The result of cultivation in those plants which serve as food is to produce in them those constituents of the blood. In the absence of the elements essential to these in the soil, starch, sugar, and woody fibre are perhaps formed, but no vegetable fibrine, albumin, or casein. If we intend to produce on a given surface of soil more of these latter matters than the plants can obtain from the atmosphere or receive from the soil of the same surface in its uncultivated and normal state, we must create an artificial atmosphere and add the needed elements to the soil. The nourishment which must be supplied in a given time to different plants in order to admit a free and unimpeded growth is very unequal. On pure sand, on calcareous soil, on naked rocks, only a few genera of plants prosper, and these are, for the most part, perennial plants. They require for their slow growth only such minute quantities of mineral substances as the soil can furnish, which may be totally barren for other species. Annual, and especially summer plants, grow and attain their perfection in a comparatively short time. They therefore do not prosper on a soil which is poor in those mineral substances necessary to their development. To attain a maximum in height in the short period of their existence, the nourishment contained in the atmosphere is not sufficient. If the end of cultivation is to be obtained, we must create in the soil an artificial atmosphere of carbonic acid and ammonia, and this surplus of nourishment, which the leaves cannot appropriate from the air, must be taken up by the corresponding organs, i.e. the roots, from the soil. But the ammonia, together with the carbonic acid, are alone insufficient to become part of a plant destined to the nourishment of animals. In the absence of the alkalis, the phosphates and other earthly salts, no vegetable fibrine, no vegetable casein can be formed. The phosphoric acid of the phosphate of lime, indispensable to the cerealia and other vegetables in the formation of their seeds, is separated as an excrement in great quantities by the rind and barks of ligneous plants. How different are the evergreen plants, the cacti, the mosses, the ferns and the pines, from our annual grasses, the cerealia and leguminous vegetables. The former, at every time of the day during winter and summer, obtain carbon through their leaves by absorbing carbonic acid, which is not furnished by the barren soil on which they grow. Water is also absorbed and retained by their coriaceous or fleshy leaves with great force. They lose very little by evaporation compared with other plants. On the other hand, how very small is the quantity of mineral substances which they withdraw from the soil during their almost constant growth in a year, in comparison with the quantity which one crop of wheat of an equal weight receives in 3 months. It is by means of moisture that plants receive the necessary alkalis and salts from the soil. In dry summers a phenomenon is observed which, when the importance of mineral elements to the life of a plant was unknown, could not be explained. The leaves of plants, first developed and perfected, and therefore nearer the surface of the soil, shrivel up and become yellow, lose their vitality, and fall off, while the plant is in an active state of growth, without any visible cause. This phenomenon is not seen in moist years, nor in evergreen plants, and but rarely in plants which have long and deep roots, nor is it seen in perennials in autumn and winter. The cause of this premature decay is now obvious. The perfectly developed leaves absorb continually carbonic acid and ammonia from the atmosphere, which are converted into elements of new leaves, buds and shoots, but this metamorphosis cannot be effected without the aid of the alkalis and other mineral substances. If the soil is moist, the latter are continually supplied to an adequate amount, and the plant retains its lively green colour. But if this supply ceases from a want of moisture to dissolve mineral elements, a separation takes place in the plant itself. The mineral constituents of the juice are withdrawn from the leaves already formed, and are used for the formation of the young shoots, and as soon as the seeds are developed, the vitality of the leaves completely ceases. These withered leaves contain only minute traces of soluble salts, while the buds and shoots are very rich in them. On the other hand, it has been observed that where a soil is too highly impregnated with soluble saline materials, these are separated upon the surface of the leaves. This happens to culinary vegetables especially, whose leaves become covered in a white crust. In consequence of these exudations, the plant sickens. Its organic activity decreases, its growth is disturbed, and if this state continues long, the plant dies. This is most frequently seen in foliaceous plants, the large surface of which evaporate considerable quantities of water. Carrots, pumpkins, peas, etc. are frequently thus diseased, when, after dry weather, the plant being near its full growth, the soil is moistened by short showers, followed again by dry weather. The rapid evaporation carries off the water absorbed by the root, and this leaves the salt in the plant in a far greater quantity than it can assimilate. These salts effloresce upon the surface of the leaves, and if they are herbaceous and juicy, produce an effect upon them as if they had been watered with a solution containing a greater quantity of salts than their organism can bear. Of two plants of the same species, this disease befalls that which is nearest its perfection. If one should have been planted later, or be more backwards in its development, the same external cause which destroys the one will contribute to the growth of the other. End of section 11. Section 12 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larysa Jaworski, Brisbane, Australia, March 2007. Familiar Letters on Chemistry by Justus LIEBIG. Letter 12. My dear Sir, having now occupied several letters with the attempt to unravel, by means of chemistry, some of the most curious functions of the animal body, and, as I hope, made clear to you the distinctions between the two kinds of constituent elements in food and the purposes they severally subserve in sustaining life, let me now direct your attention to a scarcely less interesting and equally important subject, the means of obtaining from a given surface of the earth the largest amount of produce adapted to the food of man and animals. Agriculture is both a science and an art. The knowledge of all the conditions of life of vegetables, the origin of their elements, and the sources of their nourishment, forms its scientific basis. From this knowledge we derive certain rules for the exercise of art, the principles upon which the mechanical operations of farming depend. The usefulness or necessity of these for preparing the soil to support the growth of plants and for removing every obnoxious influence. No experience, drawn from the exercise of the art, can be opposed to true scientific principles, because the latter should include all the results of practical operations, and are in some instances solely derived therefrom. Theory must correspond with experience, because it is nothing more than the reduction of a series of phenomena to their last causes. A field in which we cultivate the same plant for several successive years becomes barren for that plant in a period varying with the nature of the soil. In one field it will be in 3, in another in 7, in a third in 20, in a fourth in 100 years. One field bears wheat and no peas, another beans or turnips but no tobacco. A third gives a plentiful crop of turnips, but will not bear clover. What is the reason that a field loses its fertility for one plant, the same which at first flourished there? What is the reason one kind of plant succeeds in a field where another fails? These questions belong to science. What means are necessary to preserve a field its fertility for one and the same plant? What to render one field fertile for 2 or 3 for all plants? These last questions are put by art, but they cannot be answered by art. If a farmer, without the guidance of just scientific principles, is trying experiments to render a field fertile for a plant which it otherwise will not bear, his prospect of success is very small. Thousands of farmers try such experiments in various directions, the result of which is a mass of practical experience forming a method of cultivation which accomplishes the desired end for certain places. But the same method frequently does not succeed. It indeed ceases to be applicable to a second or third place in the immediate neighbourhood. How large a capital and how much power are wasted in these experiments! Very different and far more secure is the path indicated by science. It exposes us to no danger of failing, but on the contrary it furnishes us with every guarantee of success. If the cause of failure, of barrenness in the soil for one or two plants has been discovered, means to remedy it may be found. The most exact observations prove that the method of cultivation must vary with the geognostical condition of the subsoil. In basalt, greywacke, porphyry, sandstone, limestone, etc., are certain elements indispensable to the growth of plants, and in the presence of which renders them fertile. This fully explains the difference in the necessary methods of culture for different places, since it's obvious that the essential elements of the soil must vary with the varieties of composition of the rocks, from the disintegration of which they originated. Wheat, clover, and turnips, for example, each require certain elements from the soil. They will not flourish where the appropriate elements are absent. Science teaches us what elements are essential to every species of plants by an analysis of their ashes. If therefore a soil is found wanting of any of those elements, we discover it at once the cause of its barrenness, and its removal may now be readily accomplished. The empiric attributes all his success to the mechanical operations of agriculture. He experiences and recognises their value without inquiring what are the causes of their utility, their mode of action, and yet this scientific knowledge is of the highest importance for regulating the application of power and the expenditure of capital, for ensuring its economic expenditure and the prevention of waste. Can it be imagined that the mere passing of the ploughshare or the harrow through the soil, the mere contact of the iron, can impart fertility miraculously? Nobody, perhaps seriously, entertains such an opinion. Nevertheless, the modus operandi of these mechanical operations is by no means generally understood. The fact is quite certain that careful ploughing exerts the most favourable influence. The surface is thus mechanically divided, changed, increased, and renovated, but the ploughing is only auxiliary to the end sought. In the effects of time, in what in agriculture are technically called fallows, the repose of the fields, we recognise by science certain chemical actions which are continually exercised by the elements of the atmosphere upon the whole surface of our globe. By the action of its oxygen and its carbonic acid, aided by water, rain, changes of temperature, etc., certain elementary constituents of rocks, or of their ruins which forms the soil capable of cultivation, are rendered soluble in water and consequently become separable from all their insoluble parts. These chemical actions poetically denominates the tooth of time, destroy all the works of man and gradually reduce the hardest rocks to the condition of dust. By their influence the necessary elements of the soil become fitted for assimilation by plants, and it's precisely the end which is obtained by the mechanical operations of farming. They accelerate the decomposition of the soil in order to provide a new generation of plants with the necessary elements in a condition favourable to their assimilation. It is obvious that the rapidity of the decomposition of a solid body must increase with the extension of its surface. The more points of contact we offer in a given time to the external chemical agent, the more rapid will be its action. The chemist, in order to prepare a mineral for analysis, to decompose it or to increase the solubility of its elements, proceeds in the same way as the farmer deals with his fields. He spares no labour in order to reduce it to the finest powder. He separates the impalpable from the coarser parts by washing, and repeats his mechanical bruising and trituration, being assured his whole process will fail if he is inattentive to this essential and preliminary part of it. The influence which the increase of surface exercises upon the integration of rocks, and upon the chemical action of air and moisture, is strikingly illustrated upon a large scale in the operations pursued by the gold mines of Yearsley in Chile. These are described in a very interesting manner by Darwin. The rock containing the gold ore is pounded by mills into the finest powder. This is subjected to washing, which separates the lighter particles from the metallic. The gold sinks to the bottom, while a stream of water carries away the lighter, earthy parts into ponds, where it subsides to the bottom as mud. When this deposit has gradually filled up the pond, This mud is taken out and piled in heaps and left exposed to the action of the atmosphere and moisture. The washing completely removes all the soluble part of the disintegrated rock. The insoluble part, moreover, cannot undergo any further change while it is covered with water, and so excluded from the influence of the atmosphere at the bottom of the pond. But, being exposed at once to the air and moisture, a powerful chemical action takes place in the whole mass, which becomes indicated by an efflorescence of salts covering the whole surface of the heaps in considerable quantity. After being exposed for 2 to 3 years, the mud is again subject to the same process of washing, and a considerable quantity of gold is obtained, this having been separated by the chemical process of decomposition in the mass. The exposure and washing of the same mud is repeated 6 or 7 times, and at every washing it furnishes a new quantity of gold, although its amount diminishes every time. Precisely similar is the chemical action which takes place in the soil of our fields, and we accelerate and increase it by the mechanical operations of our agriculture. By these we sever and extend the surface, and endeavour to make every atom of the soil accessible to the action of carbonic acid and oxygen of the atmosphere. We thus produce a stock of soluble mineral substances, which serves as nourishment to a new generation of plants, materials which are indispensable to their growth and prosperity. End of section 12. Section 13 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larysa Jaworski, Brisbane, Australia, March 2007. Familiar Letters on Chemistry by Justus LIEBIG. Letter 13. My dear Sir, having in my last letter spoken of the general principles upon which the science and art of agriculture must be based, let me now direct your attention to some of those particulars between chemistry and agriculture, and demonstrate the impossibility of perfecting the important art of rearing food for man and animals without a profound knowledge of our science. All plants cultivated as food require for their healthy sustenance the alkalis and alkaline earths, each in a certain proportion, and in addition to these the cerealia do not succeed in a soil destitute of silica in a soluble condition. The combinations of this substance found as natural productions, namely the silicates, differ greatly in the degree of facility with which they undergo decomposition, in consequence of their unequal resistance opposed by their integral parts to the dissolving power of the atmospheric agencies. Thus the granite of Corsica degenerates into a powder in time which scarcely suffices to deprive the polished granite of Heidelberg of its lustre. Some soils abound in silicates, so readily decomposable that in every 1 or 2 years as much silicate of potash becomes soluble and fitted for assimilation as is required by the leaves and straw of a crop of wheat. In Hungary, extensive districts are not uncommon where wheat and tobacco have been grown alternately upon the same soil for centuries, the land never receiving back any of those mineral elements which were withdrawn in the grain and straw. On the other hand, there are fields in which the necessary amount of soluble silicate of potash for a single crop of wheat is not separated from the insoluble masses in the soil less than 2, 3, or even more years. The term fallow in agriculture designates that period in which the soil, left to the influence of the atmosphere, becomes enriched with those soluble mineral constituents. Fallow, however, does not generally imply the entire cessation of cultivation, but only an interval in the growth of the cerealia. That store of silicates and alkalis, which is the principal condition of their success, is obtained if potatoes or turnips are grown upon the same fields in the intermediate periods, since these crops do not abstract a particle of silica and therefore leave the field equally fertile for the following crop of wheat. The preceding remarks will render it obvious to you that the mechanical working of the soil is the simplest and cheapest method of rendering the elements of nutrition contained in it accessible to plants. But it may be asked, are there not other means of decomposing the soil besides its mechanical subdivision? Are there not substances which, by their chemical operation, will equally well or better render its constituents suitable for entering into vegetable organisms? Yes, we certainly possess such substances, and one of them, namely quicklime, has been employed for the last century past in England for this purpose, and it would be difficult to find a substance better adapted to this service, as it is simple and in almost all localities cheap and easily accessible. In order to obtain correct views respecting the effect of quicklime upon the soil, let me remind you of the first process employed by the chemist when he is desirous of analysing a mineral, and for this purpose wishes to bring its elements into a soluble state. Let the mineral to be examined be, for instance, feldspar. This substance, taken alone, even when reduced to the finest powder, requires for its solution to be treated with an acid for weeks or months. But if we first mix it with quicklime, and expose the mixture to a moderately strong heat, the lime enters into chemical combination with certain elements of the feldspar, and its alkali, or potass, is set free. And now the acid, even without heat, dissolves not only the lime, but also so much of the silica of feldspar as to form a transparent jelly. The same effect which the lime in this process, with the aid of heat, exerts upon the feldspar, it produces when it is mixed with the alkaline argillaceous silicates, and they are for a long time kept together in a moist state. Common potter's clay or pipe clay, diffused through water and added to milk of lime, thickens immediately upon mixing, and if the mixture is kept for some months, then treated with acid, the clay becomes gelatinous, which would not occur without the admixture with the lime. The lime, in combining with the elements of the clay, liquefies it, and, what is more remarkable, liberates the greater part of its alkalis. These interesting facts were first observed by Fuchs at Munich. They have not only led to a more intimate knowledge of the nature and properties of the hydraulic cements, but, what is far more important, they explain the effects of caustic lime upon the soil, and guide the agriculturist in the application of an invaluable means of opening it, and setting free its alkalis, substances so important, nay, so indispensable to its crops. In the month of October, the fields of Yorkshire and Oxfordshire look as if they were covered with snow. Whole square miles are seen whitened over with quicklime, which during the moist winter months exercises its beneficial influence upon the stiff clayey soil of those counties. According to the humus theory, quicklime ought to exert the most noxious influence upon the soil, because all organic matters contained in it are destroyed by it, and rendered incapable of yielding their humus to a new vegetation. The facts are indeed directly contrary to this now abandoned theory. The fertility of the soil is increased by the lime. The cerealia require the alkalis and alkaline silicates, which the action of the lime renders fit for assimilation by the plants. If in addition to these there is any decaying organic matter present in the soil supplying carbonic acid, it may facilitate their development, but it is not essential to their growth. If we furnish the soil with ammonia and the phosphates which are indispensable to the cerealia with the alkaline silicates, we have all the conditions necessary to ensure an abundant harvest. The atmosphere is an inexhaustible source of carbonic acid. A no less favourable influence than that of lime is exercised upon the soil of peaty land by the mere act of burning it. This greatly enhances its fertility. We have not long been acquainted with the remarkable change which the properties of clay undergo by burning. The observation was first made in the process of analysing the clay silicates. Many of these in their natural state are not acted on by acids, but they become perfectly soluble if heated to redness before the application of the acid. This property belongs to potter's clay, pipe clay, loam, and many different modifications of clay in soils. In their natural state they may be boiled in concentrated sulphuric acid without sensible change, but if feebly burned, as is done with the pipe clay in many alum manufactories, They dissolve in the acid with the greatest facility, the contained silica being separated like jelly in a soluble state. Potter's clay belongs to the most sterile kinds of soil, and yet it contains within itself all the constituent elements essential to a most luxurious growth of plants, but their mere presence is insufficient to secure this end. The soil must be accessible to the atmosphere, to its oxygen, to its carbonic acid. They must penetrate it in order to secure the conditions necessary to a happy and vigorous development of the roots. The elements present must be brought into this particular state of combination which will enable them to enter into plants. Plastic clay is wanting in these properties, but they are imparted to it by a feeble calcination. At Hardwicke Court, near Gloucester, I have seen a garden, Mr. Baker's, consisting of a stiff clay which was perfectly sterile, become by mere burning extremely fertile. The operation was extended to a depth of 3 feet. This was an expensive process, certainly, but it was effectual. The great difference in the properties of burnt and unburnt clay is illustrated by what is seen in brick houses built in moist situations. In the town of Flanders, for instance, where most buildings are brick, efflorescences of salts cover the surfaces of the walls like a white nap within a few days after they are erected. If this saline incrustation is washed away by the rain, it soon reappears, and this is even observed on walls which, like the gateway of Lisle, have been erected for centuries. These saline incrustations consist of carbonates and sulfates with alkaline bases, and it is well known that these act an important part in vegetation. The influence of lime in their production is manifested by their appearing first at the place where the mortar and brick come into contact. It will now be obvious to you that in a mixture of clay with lime, all the conditions exist for the solution of the silicated clay, and the solubility of the alkaline silicates. The lime gradually dissolving in water charged with carbonic acid acts like milk of lime upon the clay. This explains also the favourable influence which marl, by which term all those varieties of clay rich in chalk are designated, exerts upon most kinds of soil. There are marly soils which surpass all others in fertility for all kinds of plants, but I believe marl in a burnt state must be far more effective, as well as other materials possessing a similar composition, as, for instance, those species of limestone which are adapted to the preparation of hydraulic cements, for these carry to the soil not only the alkaline bases useful to plants, but also silica in a state capable of assimilation. The ashes of coals and lignite are also excellent means of ameliorating the soil, and they are used in many places for this purpose. The most suitable may be readily known by their property of forming a gelatinous mass when treated with acids, or by becoming, when mixed with cream of lime, like hydraulic cement, solid and hard as stone. I have now, I trust, explained to your satisfaction that the mechanical operations of agriculture, the application of lime and chalk to lands, and the burning of clay depend upon one and the same scientific principle. They are means of accelerating the decomposition of the alkaline clay silicates in order to provide plants at the beginning of a new vegetation with certain inorganic matters indispensable for their nutrition. End of section 13.
Section 14 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Familiar Letters on Chemistry by Justus Liebig, Letter 14. Nature and Effects of Manures. Animal bodies subject to constant waste. Parts separating. Exuviae, waste vegetable matters, together all contain the elements of the soil and of food. Various value of excrements of different animals as manure. My dear Sir, I treated, in my last letter, of the means of improving the condition of the soil for agricultural purposes by mechanical operations and mineral agents. I have now to speak of the uses and effects of animal exuviae, and vegetable matters, or manures properly so called. In order to understand the nature of these, and the peculiarity of their influence upon our fields, it is highly important to keep in mind the source whence they are derived. It is generally known that if we deprive an animal of food, the weight of its body diminishes during every month of its existence. If this abstinence is continued for some time, the diminution becomes apparent to the eye. All the fat of the body disappears, the muscles decrease in firmness and bulk, and if the animal is allowed to die starved, scarcely anything but skin, tendon, and bones remain. This emaciation which occurs in a body otherwise healthy demonstrates to us that during the life of an animal every part of its living substance is undergoing a perpetual change. All its component parts, assuming the form of lifeless compounds, are thrown off by the skin, lungs, and urinary system, altered more or less by the secretory organs. This change in the living body is intimately connected with the process of respiration. It is, in truth, occasioned by the oxygen of the atmosphere in breathing, which combines with all the various matters within the body. At every inspiration a quantity of oxygen passes into the blood in the lungs, and unites with its elements. But although the weight of the oxygen thus daily entering into the body amounts to 32 or more ounces, yet the weight of the body is not thereby increased. Exactly as much oxygen as is imbibed in inspiration passes off in expiration, in the form of carbonic acid and water, so that with every breath the amount of carbon and hydrogen in the body is diminished. But the emaciation, the loss of weight by starvation, does not simply depend upon the separation of the carbon and hydrogen, but all the other substances which are in combination with these elements in the living tissues pass off in the secretions. The nitrogen undergoes a change, and is thrown out of the system by the kidneys. Their secretion, the urine, contains not only a compound rich in nitrogen, namely urea, but the sulphur of the tissues in the form of a sulphate, all the soluble salts of the blood and animal fluids, common salt, the phosphates, soda, and potash. The carbon and hydrogen of the blood, of the muscular fibre, and of all the animal tissues which can undergo change, return into the atmosphere. The nitrogen and all the soluble inorganic elements are carried into the earth in the urine. These changes take place in the healthy animal body during every moment of life. A waste and loss of substance proceeds continually, and if this loss is to be restored, and the original weight and substance repaired, an adequate supply of materials must be furnished, from whence the blood and wasted tissue may be regenerated. This supply is obtained from the food. In an adult person in a normal or healthy condition, no sensible increase or decrease of weight occurs from day to day. In youth the weight of the body increases, whilst in old age it decreases. There can be no doubt that in the adult the food has exactly replaced the loss of substance. It has supplied just so much carbon, hydrogen, nitrogen, and other elements as have passed through the skin, lungs, and urinary organs. In youth the supply is greater than the waste. Part of the elements of the food remain to augment the bulk of the body. In old age the waste is greater than the supply, and the body diminishes. It is unquestionable that, with the exception of a certain quantity of carbon and hydrogen, which are secreted through the skin and lungs, we obtain, in the solid and fluid excrements of man and animals, all the elements of their food. We obtain daily, in the form of urea, all the nitrogen taken in the food, both of the young and the adult, and further in the urine, the whole amount of the alkalis, soluble phosphates, and sulphates contained in all the various aliments. In the solid excrements are found all those substances taken in the food which have undergone no alteration in the digestive organs, all indigestible matters, such as woody fibre, the green colouring matter of leaves, chlorophyll, wax, etc. Physiology teaches us that the process of nutrition in animals, that is, their increase of bulk, or the restoration of wasted parts, proceeds from the blood. The purpose of digestion and assimilation is to convert the food into blood. In the stomach and intestines, therefore, all those substances in the food capable of conversion into blood are separated from its other constituents. In other words, during the passage of the food through the intestinal canal, there is a constant absorption of its nitrogen, since only azotized substances are capable of conversion into blood, and therefore the solid excrements are destitute of that element, except only a small portion in the constitution of that secretion which is formed to facilitate their passage. With the solid excrements, the phosphates of lime and magnesia, which are contained in the food and not assimilated, are carried off, these salts being insoluble in water and therefore not entering the urine. We may obtain a clear insight into the chemical constitution of the solid excrements without further investigation by comparing the faeces of a dog with his food. We give that animal flesh and bones, substances rich in azotized matter, and we obtain, as the last product of its digestion, a perfectly white excrement, solid while moist, but becoming in dry air a powder. This is the phosphate of lime of the bones, with scarcely 1% of foreign organic matter. Thus we see that in the solid and fluid excrements of man and animals, all the nitrogen, in short, all the constituent ingredients of the consumed food, soluble and insoluble, are returned, and as food is primarily derived from the fields, we possess in those excrements all the ingredients which we have taken from it in the form of seeds, roots, or herbs. One part of the crops employed for fattening sheep and cattle is consumed by man as animal food. Another part is taken directly, as flour, potatoes, green vegetables, etc. A third portion consists of vegetable refuse and straw employed as litter. None of the materials of the soil need be lost. We can, it is obvious, get back all its constituent parts which have been withdrawn therefrom, as fruits, grains, and animals, in the fluid and solid excrements of man and the bones, blood, and skins of the slaughtered animals. It depends upon ourselves to collect carefully all these scattered elements, and to restore the disturbed equilibrium of composition in the soil. We can calculate exactly how much and which of the component parts of the soil we export in a sheep or an ox, in a quarter of barley, wheat, or potatoes; and we can discover, from the known composition of the excrements of man and animals, how much we have to supply to restore what is lost to our fields. If, however, we could procure from other sources the substances which we give to the exuviae of man and animals their value in agriculture, we should not need the latter. It is quite indifferent for our purposes whether we supply the ammonia, the source of nitrogen, in the form of urine, or in that of a salt derived from coal tar; whether we derive the phosphate of lime from bones, apatite, or fossil excrements. The principal problem for agriculture is, how to replace those substances which have been taken from the soil, and which can be furnished by the atmosphere. If the manure supplies an imperfect compensation for this loss, the fertility of a field or of a country decreases. If, on the contrary, more are given to the fields, their fertility increases. An importation of urine or of solid excrements from a foreign country is equivalent to an importation of grain and cattle. In a certain time the elements of those substances assume the form of grain or of fodder, then become flesh and bones, enter into the human body, and return again day by day to the form they originally possessed. The only real loss of elements we are unable to prevent is of the phosphates, and these, in accordance with the customs of all modern nations, are deposited in the grave. For the rest, every part of that enormous quantity of food which a man consumes during his lifetime, say in 60 or 70 years, which was derived from the fields, can be obtained and returned to them. We know with absolute certainty that in the blood of a young or growing animal there remains a certain quantity of phosphate of lime and of the alkaline phosphates, to be stored up and to minister to the growth of the bones and general bulk of the body; and that, with the exception of this very small quantity, we receive back, in the solid and fluid excrements, all the salts and alkaline bases, all the phosphates of lime and magnesia, and consequently all the inorganic elements which the animal consumes in its food. We can thus ascertain precisely the quantity, quality, and composition of animal excrements without the trouble of analyzing them. If we give a horse daily 4½ pounds weight of oats, and 15 pounds of hay, and knowing that the oats give 4 per cent. And hay 9 per cent. Of ashes, we can calculate that the daily excrement of the horse will contain 21 ounces of inorganic matter which was drawn from the fields. By analysis we can determine the exact relative amount of silica, of phosphates, and of alkalis contained in the ashes of the oats and of the hay. You will now understand that the constituents of the solid parts of animal excrements, and therefore their qualities as manure, must vary with the nature of the creature's food. If we feed a cow upon beetroot or potatoes without hay, straw, or grain, there will be no silica in her solid excrements, but there will be phosphate of lime and magnesia. Her fluid excrements will contain carbonate of potash and soda, together with compounds of the same bases with inorganic acids. In one word, we have, in the fluid excrements, all the soluble parts of the ashes of the consumed food, and in the solid excrements all those parts of the ashes which are insoluble in the water. If the food, after burning, leaves behind ashes containing soluble alkaline phosphates, as is the case with bread, seeds of all kinds, and flesh, we obtain from the animal by which they were consumed a urine holding in solution these phosphates. If, however, the ashes of food contain no alkaline phosphates, but abound in insoluble earthy phosphates, as hay, carrots, and potatoes, the urine will be free from alkaline phosphates, but the earthy phosphates will be found in the feces. The urine of man, of carnivorous and graminivorous animals contain alkaline phosphates; that of herbivorous animals is free from these salts. The analysis of the excrements of man, of the piscivorous birds, as the guano, of the horse, and of cattle, furnishes us with a precise knowledge of the salts they contain, and demonstrates that in those excrements we return to the fields the ashes of the plants which have served as food, the soluble and insoluble salts and earths indispensable to the development of cultivated plants, and which must be furnished to them by a fertile soil. There can be no doubt that, in supplying these excrements to the soil, we return to it those constituents which the crops have removed from it, and we renew its capability of nourishing new crops. In one word, we restore the disturbed equilibrium, and consequently, knowing that the elements of the food derived from the soil enter into the urine and solid excrements of the animals it nourishes, we can with the greatest facility determine the exact value of the different kinds of manure. Thus the excrement of pigs which have been fed with peas and potatoes are principally suited for manuring crops of potatoes and peas. In feeding a cow upon hay and turnips, we obtain a manure containing the inorganic elements of grasses and turnips, and which is therefore preferable for manuring turnips. The excrement of pigeons contains the mineral elements of grain; that of rabbits, the elements of herbs and kitchen vegetables. The fluid and solid excrements of man, however, contain the mineral elements of grain and seeds in the greatest quantity. Section 15
of Familiar Letters on Chemistry, This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gilberd, 2007. Familiar Letters on Chemistry by Justus Liebig. Letter number 15. My dear Sir, you are now acquainted with my opinions respecting the effects of the application of mineral agents to our cultivated fields, and also the rationale of the influence of the various kinds of manures. You will, therefore, now readily understand what I have to say of the sources whence the carbon and nitrogen, indispensable to the growth of plants, are derived. The growth of forests and the produce of meadows demonstrate that an inexhaustible supply of carbon is furnished for vegetation by the carbonic acid of the atmosphere. We obtain from an equal surface of forest or meadowland, where the necessary mineral elements of the soil are present in a suitable state, and to which no carbonaceous matter whatever is furnished in manures, an amount of carbon, in the shape of wood and hay, quite equal, and ofttimes more than is produced by our fields in grain, roots, and straw, upon which abundance of manure has been heaped. It is perfectly obvious that the atmosphere must furnish to our cultivated fields as much carbonic acid as it does to an equal surface of forest or meadow, and that the carbon of this carbonic acid is assimilated, or may be assimilated, by the plants growing there, provided the conditions essential to its assimilation and becoming a constituent element of vegetables exist in the soil of these fields. In many tropical countries, the produce of the land in grain or roots during the whole year depends upon one rain in the spring. If this rain is deficient in quantity or altogether wanting, the expectation of an abundant harvest is diminished or destroyed. Now it cannot be the water merely which produces this enlivening and fertilizing effect observed, and which lasts for weeks and months. The plant receives, by means of this water, at the time of its first development, the alkalis, alkaliners, and phosphates necessary to its organization. If these elements, which are necessary previous to its assimilation of atmospheric nourishment, be absent, its growth is retarded. In fact, the development of a plant is in a direct ratio to the amount of matter it takes up from the soil. If, therefore, a soil is deficient in these mineral constituents required by plants, they will not flourish, even with an abundant supply of water. The produce of carbon on a meadow, or an equal surface of forest land, is independent of a supply of carbonaceous manure, but it depends upon the presence of certain elements of the soil, which in themselves contain no carbon, together with the existence of conditions under which their assimilation by plants can be effected. We increase the produce of our cultivated fields in carbon by a supply of lime, ashes, and marl, substances which cannot furnish carbon to the plants. And yet it is indisputable, being founded upon abundant experience, that in these substances we furnish to the fields elements which greatly increase the bulk of their produce and consequently the amount of carbon. If we admit these facts to be established, we can no longer doubt that a deficient produce of carbon, or in other words, the bareness of a field, does not depend upon carbonic acid, because we are able to increase the produce to a certain degree by a supply of substances which do not contain any carbon. The same source whence the meadow and the forest are furnished with carbon is also open to our cultivated plants. The great object of agriculture, therefore, is to discover the means best adapted to enable these plants to assimilate the carbon of the atmosphere which exists in it as carbonic acid. In furnishing plants, therefore, with mineral elements, we give them the power to approximate carbon from a source which is inexhaustible, whilst in the absence of these elements the most abundant supply of carbonic acid, or of decaying vegetable matter, would not increase the produce of a field. With an adequate and equal supply of these essential mineral constituents in the soil, the amount of carbonic acid absorbed by a plant from the atmosphere in a given time is limited by the quantity which is brought into contact with its organs of absorption. The withdrawal of carbonic acid from the atmosphere by the vegetable organism takes place chiefly through its leaves. This absorption requires the contact of the carbonic acid with their surface, or with the parts of the plant by which it is absorbed. The quantity of carbonic acid absorbed in a given time is in direct proportion to the surface of the leaves and the amount of carbonic acid contained in the air. That is, two plants of the same kind and the same extent of surface absorption in equal times and under equal conditions absorb one and the same amount of carbon. In an atmosphere containing a double portion of carbonic acid, a plant absorbs, under the same condition, twice the quantity of carbon. Boussingault observed that the leaves of the vine, enclosed in a vessel, withdrew all the carbonic acid from a current of air which was passed through it, however great its velocity. Dumas Lecon, page 23. If, therefore, we supply double the quantity of carbonic acid to one plant, the extent of the surface of which is only half that of another living in ordinary atmospheric air, the former will obtain and approximate as much carbon as the latter. Hence results the effect of humus and all decaying organic substances upon vegetation. If we suppose all the conditions for the absorption of carbonic acid present, a young plant will increase in mass in a limited time only in proportion to its absorbing surface. But if we create in the soil a new source of carbonic acid by decaying vegetable substances, the roots absorb in the same time 3 times as much carbonic acid from the soil as the leaves derive from the atmosphere. The plant will increase in weight fourfold. This fourfold increase extends to the leaves, buds, stalks, etc. And in the increased extent of the surface, the plant acquires an increased power of absorbing nourishment from the air, which continues in action far beyond the time when its derivation of carbonic acid through the roots ceases. Humus, as a source of carbonic acid in cultivated lands, is not only useful as a means of increasing the quantity of carbon, an effect which in most cases may be indifferent for agricultural purposes, but the mass of the plant having increased rapidly in a short time, space is obtained for the assimilation of the elements of the soil necessary for the formation of new leaves and branches. Water evaporates incessantly from the surface of the young plant. Its quantity is in direct proportion to the temperature and the extent of the surface. The numerous radical fibrillate replace, like so many pumps, the evaporated water, and so long as the soil is moist or penetrated with water, the indispensable elements of the soil dissolved in the water are supplied to the plant. The water absorbed by the plant evaporating in an aeriform state leaves the saline and other mineral constituents within it. The relative proportion of these elements taken up by a plant is greater, the more extensive the surface and more abundant the supply of water. Where these are limited, the plant soon reaches its full growth, while if their supply is continued, a greater amount of elements necessary to enable it to appropriate atmospheric nourishment being obtained, its development proceeds much further. The quantity or mass of seed produced will correspond to the quantity of mineral constituents present in the plant. That plant, therefore, containing the most alkaline phosphates and earthy salts, will produce more or a greater weight of seeds than another which in equal time has absorbed less of them. We consequently observe, in a hot summer, when a further supply of mineral ingredients from the soil ceases through want of water, that the height and strength of plants, as well as the development of their seeds, are in direct proportion to its absorption of the elementary parts of the soil in the preceding epochs of its growth. The fertility of the year depends in general upon the temperature and the moisture or dryness of the spring. If all the conditions necessary to the assimilation of the atmospheric nourishment be secured to our cultivated plants, the action of humus then, as we have explained it above, is chiefly of value in gaining time. In agriculture this must ever be taken into account, and in this respect humus is of importance in favouring the growth of vegetables, cabbages, etc. But the cerealia and plants grown for their roots meet on our fields in the remains of the preceding crop with a quantity of decaying vegetable substances corresponding to their contents of mineral nutriment from the soil, and consequently with a quantity of carbonic acid adequate to their accelerated development in the spring. A further supply of carbonic acid, therefore, would be quite useless without a corresponding increase of mineral ingredients. From a morgen of good meadowland, 2,500 pounds weight of hay, according to the best agriculturists, are obtained on an average. This amount is furnished without any supply of organic substances, without manure containing carbon or nitrogen, by irrigation and the application of ashes or gypsum. Double that amount may be grown, but assuming 2,500 pounds weight of hay to be the maximum, we may calculate the amount of carbon and nitrogen derived from the atmosphere by the plants of the meadow. According to elementary analysis, hay, dried at a temperature of 100 degrees Reaumur, contains 45.8% of carbon and 1.5% of nitrogen. 14% of water retained by the hay, dried at common temperatures, is driven off at 100 degrees. 2,500 pounds weight of hay, therefore, corresponds to 2,150 pounds dried at 100 degrees. This shows us that 984 pounds of carbon and 32.2 pounds weight of nitrogen have been obtained in the produce of 1 morgen of meadowland. Suppose that this nitrogen has been absorbed by the plants in the form of ammonia. The atmosphere contains 39.1 pounds weight of ammonia to every 3,640 pounds weight of carbonic acid, equals 984 carbon, or 27%. Or in other words, to every 1,000 pounds weight of carbonic acid, 10.7 pounds of ammonia, that is, to about 1/100,000th the weight of the air, or 1/60,000th of its volume. For every 100 parts of carbonic acid absorbed by the surface of the leaves, the plant receives from the atmosphere somewhat more than 1 part of ammonia. With every 1,000 pounds of carbon we obtain from a meadow 32 7/10 pounds of nitrogen from cultivated fields in wheat, 21 1/2 pounds of nitrogen, oats 22.3 pounds of nitrogen, rye 15.2 pounds of nitrogen, potatoes 34.1 pounds of nitrogen, beetroot 39.1 pounds of nitrogen, clover 44 pounds of nitrogen, peas 62 pounds of nitrogen. Bossingalt obtained from his farm at Bechelbronn in Alsace in 5 years the shape of potatoes, wheat, clover, turnips, and oats, 8,383 of carbon and 250.7 nitrogen. In the following 5 years, as beetroot, wheat, clover, turnips, oats, and rye, 8,192 of carbon and 284.2 of nitrogen. In a further course of 6 years, potatoes, wheat, clover, turnips, peas, and rye 10,949 of carbon, 356.6 of nitrogen. In 16 years, 27,424 carbon, 858 and one half nitrogen, which gives us for every 1,000 carbon 31.3 nitrogen. From these interesting and unquestionable facts, we may deduce some conclusions of the highest importance in their application to agriculture. 1. We observe that the relative proportions of carbon and nitrogen stand in a field relation to the surface of the leaves. Those plants in which all the nitrogen may be said to be concentrated in the seeds, as in cerealia, contain on the whole less nitrogen than the leguminous plants, peas, and clover. 2. The produce of nitrogen on a meadow which receives no nitrogenized manure is greater than that of a field of wheat which has been manured. 3. The produce of nitrogen in clover and peas, which agriculturists will acknowledge require no nitrogenized manure, is far greater than that of a potato or turnip field, which is abundantly supplied with such manures. Lastly, and this is the most curious deduction to be derived from the above facts, if we plant potatoes, wheat, turnips, peas, and clover, plants containing potash, lime, and silex, upon the same land 3 times manured, we gain in 16 years, for a given quantity of carbon, the same proportion of nitrogen which we receive from a meadow which has received no nitrogenized manure. On a morgen of meadow land we obtain in plants containing silex, lime, and potash 984 carbon, 32.2 nitrogen. On a morgen of cultivated land, in an average of 16 years, the plants containing the same mineral elements, silex, lime, and potash, 857 carbon, 26.8 nitrogen. If we add the carbon and nitrogen of the leaves of the beetroot and the stalk and leaves of the potato, which have not been taken into account, it still remains evident that the cultivated fields, notwithstanding the supply of carbonaceous and nitrogenized manures, produce no more carbon and nitrogen than an equal surface of meadowland supplied only with mineral elements. What then is the rationale of the effect of manure, of the solid and fluid excrements of animals? This question can now be satisfactorily answered. That effect is the restoration of the elementary constituents of the soil which have been gradually drawn up from it in the shape of grain and cattle. If the land I am speaking of had not been manured during those 16 years, not more than 1/2 or perhaps than 1/3 part of the carbon and nitrogen would have been produced. We owe it to the animal excrements that it equaled in production the meadow land, and thus because they restored the mineral ingredients of the soil removed from the crops. All that the supply of manure accomplished was to prevent the land from becoming poorer in these than the meadow, which produces 2,500 pounds of hay. We withdraw from the meadow in this way hay as large an amount of mineral substances as we do in one harvest of grain, and we know that the fertility of the meadow is just as dependent upon the restoration of these ingredients to its soil as the cultivated land is upon manures. 2 meadows of equal surface, containing unequal quantities of inorganic elements of nourishment, other conditions being equal, are very unequally fertile. That which possesses most, furnished most hay. If we do not restore to a meadow the withdrawn elements, its fertility decreases, but its fertility remains unimpaired when a due supply of animal excrements, fluid and solid, and it not only remains the same, but may be increased by a supply of mineral substances alone, such as remain after the combustion of lignaceous plants and other vegetables, namely ashes. Ashes represent the whole nourishment which vegetables receive from the soil. By furnishing them in sufficient quantities to our meadows, we give the plants growing on them the power of condensing and absorbing carbon and nitrogen by their surface. May not the effect of the solid and fluid excrements, which are the ashes of plants and grains, which have undergone combustion in the bodies of animals and of man, be depended upon in the same cause? Should not the fertility resulting from their application be altogether independent of the ammonia they contain? Would not their effect be precisely the same in promoting the fertility of cultivated plants, if we had evaporated the urine and dried and burned the solid excrements? Surely the cerealia and leguminous plants which we cultivate must derive their carbon and nitrogen from the same source whence the gramineae and leguminous plants of the meadow obtain them. No doubt can be entertained of their capability to do so. In Virginia, upon the lowest calculation, 22 pounds weight of nitrogen were taken on the average yearly from every morgen of the wheat fields. This would amount in 100 years to 2200 pounds weight. If this were derived from the soil, every morgen of it must have contained the equivalent of 110,000 pound weight of animal excrements, assuming the latter, when dried at the temperature of boiling water, to contain 2%. In Hungary, as I remarked in a former letter, tobacco and wheat have been grown upon the same field for centuries without any supply of nitrogenized manure. Is it possible that the nitrogen essential to and entering into the composition of these crops could have been drawn from the soil? Every year renews the foliage and fruits of our forests of beech, oak, and chestnuts. The leaves, the acorns, the chestnuts are rich in nitrogen. So are coconuts, breadfruit, and other tropical productions. This nitrogen is not supplied by man. Can it indeed be derived from any other source than the atmosphere? In whatever form the nitrogen supplied to plants may be contained in the atmosphere, in whatever state it may be when absorbed from the atmosphere, it must have been derived. Did not the fields of Virginia receive their nitrogen from the same source as the wild plants? Is the supply of nitrogen in the excrement of animals quite a matter of indifference? Or do we receive back from our fields a quantity of the elements of blood corresponding to this supply? The researches of Boussingault have solved this problem in the most satisfactory manner. If, in his grand experiments, the manure which he gave to his fields was in the same state, in other words, dried at 110 degrees in a vacuum, as it was when analyzed, these fields received in 16 years 1,300 pounds of nitrogen. But we know that by drying all the nitrogen escapes which is contained in solid animal excrements, as volatile carbonate of ammonia. In this calculation, the nitrogen of the urine, which by decomposition is converted into carbonate of ammonia, has not been included. If we suppose it amounted to half as much as that in the dried excrements, this would make the quantity of nitrogen supplied to the fields 1,950 pounds. In 10 years, however, as we have seen, only 1,517 pounds of nitrogen was contained in their produce of grain, straw, roots, etc. That is, far less than was supplied in the manure. And in the same period, the same extent of surface of good meadow land, 1 hectare equals 1 Hessian morgen, which received no nitrogen in manure, 2,062 pounds of nitrogen. It is well known that in Egypt, from the deficiency of wood, the excrement of animals is dried and forms the principal fuel, and that the nitrogen from the soot of this excrement was, for many centuries, imported into Europe in the form of sal ammoniac, until a method of manufacturing this substance was discovered at the end of the last century by Gravenhorst of Brunswick. The fields in the delta of the Nile are supplied with no other animal manures than the ashes of the burnt excrements, and yet they have been proverbially fertile from a period earlier than the first dawn of history, and that fertility continues to the present day as admirable as it was in the earliest times. These fields receive every year from the inundation of the Nile a new soil, in its mud deposited over their surface, rich in those mineral elements which have been withdrawn by the crops of the previous harvest. The mud of the Nile contains as little nitrogen as the mud derived from the Alps of Switzerland, which fertilizes our fields after the inundations of the Rhine. If this fertilized mud owed its property to nitrogenized matters, what enormous beds of animals and vegetables, excavae and remains, ought to exist in the mountains of Africa, in heights extending beyond the limits of perpetual snow, where no bird, no animal finds food from the absence of all vegetation. Abundant evidence to support of the important truth we are discussing may be derived from other well-known facts. Thus, the trade of Holland in cheese may be adduced in proof and illustration thereof. We know that cheese is derived from the plants which serve as food for cows. The meadowlands of Holland derive the nitrogen of cheese from the same source as with us, i.e., the atmosphere. The milch cows of Holland remain day and night on the grazing grounds, and therefore, in their fluid and solid excrements, return directly to the soil all the salts and earthy elements of their food. A very insignificant quantity only is exported in cheese. The fertility of these meadows can therefore be as little impaired as our own fields, to which we restore all the elements of the soil as manure, which have been withdrawn in the crops. The only difference is, in Holland they remain on the field, whilst we collect them at home and carry them from time to time to the fields. The nitrogen of the fluid and solid excrements of cows is derived from the meadow plants, which received it from the atmosphere. The nitrogen of the cheese also must be drawn from the same source. The meadows of Holland have, in the lapse of centuries, produced millions of hundredweights of cheese. Thousands of hundredweights are annually exported, and yet the productiveness of the meadows is in no way diminished, although they never receive more nitrogen than they originally contained. Nothing can be more certain than the fact that an exportation of nitrogenized products does not exhaust the fertility of a country, inasmuch as it is not the soil, but the atmosphere, which furnishes its vegetation with nitrogen. It follows, consequently, that we cannot increase the fertility of our fields by supply of nitrogenized manure or by salts of ammonia, but rather that their produce increases or diminishes in direct ratio with the supply of mineral elements capable of assimilation. The formulation of the constituent elements of blood, that is, of the nitrogenized principles in our cultivated plants, depends upon the presence of inorganic matters in the soil, without which no nitrogen can be assimilated, even when there is a most abundant supply. The ammonia contained in animal excrements exercises a favorable effect, inasmuch as it is accompanied by the other substances necessary to accomplish this transition into the elements of the blood. If we supply ammonia associated with all the conditions necessary to its assimilation, it ministers to the nourishment of the plants. But if this artificial supply is not given, they can derive all the needed nitrogen from the atmosphere, a source every loss from which is restored by the decomposition of the bodies of dead animals and the decay of plants. Ammonia certainly favors and accelerates the growth of plants in all soils wherein all the conditions of its assimilation are united, but it is altogether without effect as respects the production of the elements of blood. Where any of these conditions are wanting, we can suppose that asparagine, the active constituent of asparagus, the mucilaginous root of the marshmallow, the nitrogenized and sulphurous ingredients of mustard seeds, and of all cruciferous plants, may originate without the aid of the mineral elements of the soil. But if the principle of those vegetables which serve as food could be generated without the cooperation of the mineral elements of blood, without potash, soda, phosphate of lime, they would be useless to us and to herbivorous animals as food. They would not fulfill the purpose for which the wisdom of the Creator has designed them. In the absence of alkalis and phosphates, no blood, no milk, no muscular fiber can be formed. Without phosphate of lime, our horses, sheep, and cattle would be without bones. In the urine and in the solid excrement of animals we carry ammonia, and consequently nitrogen, to our cultivated plants, and this nitrogen is accompanied by all the mineral elements of food exactly in the same proportions in which both are contained in the plants which served as food to the animals, or what is the same, in those proportions in which both can serve as nourishment to a new generation of plants, to which both are essential. The effect of an artificial supply of ammonia as a source of nitrogen is therefore precisely analogous to that of humus as a source of carbonic acid. It is limited to a gain of time, that is, it accelerates the development of plants. This is of great importance and should always be taken into account in gardening, especially in the treatment of the kitchen garden, and as much as possible in agriculture on a large scale, where the time occupied in the growth of the plants cultivated is of importance. When we have exactly ascertained the quantity of ash left after the combustion of cultivated plants which have grown upon all varieties of soil, and have obtained correct analysis of these ashes, we shall learn with certainty which of the constituent elements of the plants are consistent and which are changeable, and we shall arrive at an exact knowledge of the sum of all the ingredients we withdraw from the soil in different crops. With this knowledge the farmer will be able to keep an exact record of the produce of his fields and harvest, like the account book of a well-regulated manufactory, and then by a simple calculation he can determine precisely the substances he must supply to each field, and the quantity of these in order to restore their fertility. He will be able to express in pounds weight how much of this or that element must be given in order to augment its fertility for any given kind of plants. These researches and experiments are the great desideratum of the present time. To the united efforts of the chemists of all countries we may confidently look for a solution of these great questions, and by the aid of enlightened agriculturists we shall arrive at a rational system of gardening, horticulture, and agriculture, applicable to every country and in all kinds of soil, and which will be based upon the immutable foundation of observed facts and philosophical induction. End of section 15.
Section 16 of Familiar Letters on Chemistry by Justus Liebig. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to find out how to volunteer, please contact LibriVox.org. Recorded by Peter Yearsley. Familiar Letters on Chemistry. Letter 16. My dear Sir, my recent researches into the constituent ingredients of our cultivated fields have led me to the conclusion that of all the elements furnished to plants by the soil and ministering to their nourishment, the phosphate of lime, or rather the phosphates generally, must be regarded as the most important. In order to furnish you with a clear idea of the importance of the phosphates, it may be sufficient to remind you of the fact that the blood of man and animals, besides common salt, always contains alkaline and earthy phosphates. If we burn blood and examine the ashes which remain, we find certain parts of them soluble in water and others insoluble. The soluble parts are common salt and alkaline phosphates. The insoluble consist of phosphate of lime, phosphate of magnesia, and oxide of iron. These mineral ingredients of the blood, without the presence of which in the food the formation of blood is impossible, both man and animals derive either immediately or mediately through other animals, from vegetable substances used as food. They had been constituents of vegetables. They had been parts of the soil upon which the vegetable substances were developed. If we compare the amount of the phosphates in different vegetable substances with each other, we discover a great variety, whilst there is scarcely any ashes of plants altogether devoid of them, and those parts of plants which experience has taught us are the most nutritious contain the largest proportion. To these belong all seeds and grain, especially the varieties of bread corn, peas, beans, and lentils. It is a most curious fact that if we incinerate grain or its flour, peas, beans, and lentils, we obtain ashes which are distinguished from the ashes of all other parts of vegetables by the absence of alkaline carbonates. The ashes of these seeds, when recently prepared, do not effervesce with acids. Their soluble ingredients consist solely of alkaline phosphates. The insoluble parts of phosphate of lime, phosphate of magnesia, and oxide of iron, consequently of the very same salts which are contained in blood, and which are absolutely indispensable to its formation. We are thus brought to the further indisputable conclusion that no seed suitable to become food for man and animals can be formed in any plant without the presence and co-operation of the phosphates. A field in which phosphate of lime, or the alkaline phosphates, form no part of the soil is totally incapable of producing grain, peas, or beans. An enormous quantity of these substances indispensable to the nourishment of plants is annually withdrawn from the soil and carried into great towns in the shape of flour, cattle, etc. It is certain that this incessant removal of the phosphates must tend to exhaust the land and diminish its capability of producing grain. The fields of Great Britain are in a state of progressive exhaustion from this cause, as is proved by the rapid extension of the cultivation of turnips and mangel-wurzel, plants which contain the least amount of the phosphates, and therefore require the smallest quantity for their development. These roots contain 80 to 92% of water. Their great bulk makes the amount of produce fallacious, as respects their adaptation to the food of animals, inasmuch as their contents of the ingredients of the blood, i.e. of substances which can be transformed into flesh, stands in a direct ratio to their amount of phosphates, without which neither blood nor flesh can be formed. Our fields will become more and more deficient in these essential ingredients of food in all localities where custom and habits do not admit the collection of the fluid and solid excrement of man and their application to the purposes of agriculture. In a former letter I showed you how great a waste of phosphates is unavoidable in England, and referred to the well-known fact that the importation of bones restored in a most admirable manner the fertility of the fields exhausted from this cause. In the year 1827 the importation of bones for manure amounted to 40,000 tons, and Huskisson estimated their value to be from £100,000 to £200,000 sterling. The importation is still greater at present, but it is far from being sufficient to supply the waste. Another proof of the efficacy of the phosphates in restoring fertility to exhausted land is afforded by the use of the guano, a manure which, although of recent introduction into England, has found such general and extensive application. We believe that the importation of 1 cwt. Of guano is equivalent to the importation of 8 cwt. Of wheat. The 1 cwt. Of guano assumes, in a time which can be accurately estimated, the form of a quantity of food corresponding to 8 cwt. Of wheat. The same estimate is applicable in the valuation of bones. If it were possible to restore to the soil of England and Scotland the phosphates which during the last 50 years have been carried to the sea by the Thames and the Clyde, it would be equivalent to manuring with millions of hundredweights of bones, and the produce of the land would increase 1/3 or perhaps double itself in 5 to 10 years. We cannot doubt that the same result would follow if the price of the guano admitted the application of a quantity to the surface of the fields containing as much of the phosphates as have been withdrawn from them in the same period. If a rich and cheap source of phosphate of lime and the alkaline phosphates were open to England, there can be no question that the importation of foreign corn might be altogether dispensed with after a short time. For these materials England is at present dependent upon foreign countries, and the high price of guano and of bones prevents their general application, and in sufficient quantity. Every year the trade in these substances must decrease, or their price will rise as the demand for them increases. According to these premises it cannot be disputed that the annual expense of Great Britain for the importation of bones and guano is equivalent to a duty on corn, with this difference only, that the amount is paid to foreigners in money. To restore the disturbed equilibrium of constitution of the soil, to fertilize her fields, England requires an enormous supply of animal excrements, and it must therefore excite considerable interest to learn that she possesses beneath her soil beds of fossil guano, strata of animal excrements, in a state which will probably allow of their being employed as a manure at a very small expense. The coprolithes discovered by Dr. Buckland, a discovery of the highest interest to geology, are these excrements, and it seems extremely probable that in these strata England possesses the means of supplying the place of recent bones, and therefore the principal conditions of improving agriculture, of restoring and exalting the fertility of her fields. In the autumn of 1842 Dr. Buckland pointed out to me a bed of coprolithes in the neighbourhood of Clifton, from half to 1 foot thick, enclosed in a limestone formation, extending as a brown stripe in the rocks for miles along the banks of the Severn. The limestone marl of Lyme Regis consists for the most part of 1/4 part of fossil excrements and bones. The same are abundant in the lias of Bath, Easton, and Broadway Hill, near Evesham. Dr. Buckland mentions beds several miles in extent, the substance of which consists in many places of 1/4 part of coprolithes. Pieces of the limestone rock in Clifton, near Bristol, which is rich in coprolithes and organic remains, fragments of bones, teeth, etc., were subjected to analysis, and were found to contain above 18% of phosphate of lime. If this limestone is burned and brought in that state to the fields, it must be a perfect substitute for bones, the efficacy of which as a manure does not depend, as has been generally but erroneously supposed, upon the nitrogenised matter which they contain, but on their phosphate of lime. The osseous breccia found in many parts of England deserves especial attention, as it is highly probable that in a short time it will become an important article of commerce. What a curious and interesting subject for contemplation! In the remains of an extinct animal world, England is to find the means of increasing her wealth in agricultural produce, as she has already found the great support of her manufacturing industry in fossil fuel, the preserved matter of primeval forests, the remains of a vegetable world. May this expectation be realized, and may her excellent population be thus redeemed from poverty and misery. The end of section 16, and the end of Familiar Letters on Chemistry by Justus Liebig.